Greetings everyone, welcome back to General Chemistry. I know it's been a while since the last video, because life never goes the way I plan for it to go, apparently. But, you know, it's September now, and I'm getting more and more requests from students, so I guess I'll have to slow down my pace in putting out these videos. Maybe I can get them done before winter break, but at this point, I'm not even going to try and guess how soon this is going to get done. It'll be done when it's done, but hopefully I can cover the first half of a general chemistry course before the end of the semester. That should be in time for anybody who's currently taking General Chemistry 1 in college, or AP Chemistry, or some equivalent in high school. But anyway, without further ado, let's just get straight to it. Today we are going to be talking about thermochemistry. Thermochemistry, which is not to be confused with thermodynamics. Thermochemistry and thermodynamics are different things. Thermodynamics is more complicated. For now, we're just going to start small with thermochemistry. The chemistry of heat, and I guess just energy in general. Okay, so before we start talking about the concept of heat, what we first need to establish is a couple of common terms. First is the concept of a system and the surroundings, and of course the different types of systems that exist. So a system, anytime we want to study the energy and how it moves from one thing to another, we need to define the thing that we're interested in, which we call the system. So basically the part of the universe that is being studied or being examined. Can I fit the word in there? Not gonna risk it. I'll just write it there. The part of the universe that's being examined. So, for example, if I'm interested in how long it takes for me to boil water to make my tea, then the system, the part of the universe I'm interested in that particular context, is my teapot. Actually, I don't have a teapot. What I use to make my tea is this thing right here. It's called a Turkish coffee pot. And yes, even though it's a coffee pot, I use it to make tea. I don't drink coffee, so yeah. I had to look long and hard to find that thing. They don't sell Turkish coffee pots at Target or Walmart or any of those usual IRL stores. I had to buy it online. But anyway, so that's the definition of a system. It's the part of the universe that's being examined. And the surroundings, then, are everything else. So there's the thing being studied, and then there's everything else. The surroundings, the rest of the universe. All of the universe but the system. The rest of the universe. But depending on the relationship between the system and the surroundings, you can define different types of systems. So there are three types of systems. Most chemistry teachers will not go over them, maybe because they're not particularly relevant, but I think they are. The three types of systems are the open system, which can be represented like this. The closed system, which can be represented like this. And the isolated system, which can be represented like this. Okay, so what's the difference between these? So if I were to boil water in my coffee pot here, then this would be an example of an open system. I don't have a lid on this thing. So what can happen between this coffee pot and the water inside it versus everything else around it, so basically the stove and the air in my kitchen and so on and so forth, what can happen between them is an exchange of energy, but also an exchange of matter. So I can have water boil, turn into water vapor, and then that water vapor exits my coffee pot and goes into, you know, the rest of my kitchen's air and eventually out the window to the rest of the atmosphere and so on and so forth. So matter can be exchanged between an open system and its surroundings, but so can energy. That's how I can get heat from my stove into my water. Of course, there is no water here, but use your imagination. So an open system exchanges both energy and matter, can exchange energy and matter, can exchange energy and matter with surroundings, which I'm just going to abbreviate SURR. So that's what an open system can do. And of course, you can send matter from an open system to its surroundings, or you can take matter from the surroundings to an open system. Same thing with energy. You can either send energy from the system to the surroundings or from the surroundings to the system. So it can go either way. For a closed system, imagine instead of this coffee pot, imagine if I had common sense and just bought a regular teapot for my tea. A teapot has a lid. So if you had a lid, if I had a lid for my coffee pot, or if I just bought a teapot that comes with a lid, then that would be an example of a closed system. Of course, even if it is a teapot, I would also have to close the spout, like plug it up, in order for it to be a truly closed system. But a closed system can only exchange energy with its surroundings, can only exchange energy with surroundings. So I can transfer heat into and out of a closed system, but the matter inside of a closed system stays inside. Nothing is added to it, nothing is taken from it. Can only exchange energy with surroundings. And then you've got the isolated system, which can neither exchange energy nor matter. So an isolated system can exchange neither energy nor matter. Neither energy nor matter with surroundings. So an isolated system sounds very uninteresting. It sounds like you can't really do much with an isolated system. If it can't exchange energy with the surroundings and it can't exchange matter with the surroundings, then what's the point? Well, an isolated system can sort of act like its own universe. So an isolated system could contain two or more different parts, and maybe you want to focus on one part of it and call that your subsystem, and then the rest of what's inside of your isolated system can be considered your sort of sub-surroundings. So you can have a sort of mini system and a mini surroundings within an isolated system. And this is great because, you know, it reduces the complexity. You don't have to worry about the rest of the universe as being your surroundings. You can just worry about some small set, some small part of the universe being surroundings and another small part being the system. It's like a universe in a box, sort of. Of course, true isolated systems don't exist, at least as far as I'm aware. We haven't been able to make a perfect isolated system, but we can make approximately isolated systems. You've probably used some of those special water bottles that are very resistant to changes in temperature, or you've probably used, what's it called? Why am I blanking on this? A thermos? You've probably used what's called a thermos that, you know, you fill it with your hot tea or coffee or even soup or whatever it is you want to put in there, and it kind of stays warm for a very long period of time. But of course, with enough time, even a thermos will eventually allow energy to be exchanged between its contents and its surroundings. So a thermos is not a perfectly isolated system. It's insulation, not isolation. An isolated system is basically a very, 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 very insulated system. The more insulated, the closer it is to being isolated. So, yeah, that's a thermos. What else? What's another example? For keeping things cold, ice boxes. If you've ever gone out on a picnic, well, maybe not for picnics, but when you go out for like a cookout or something, and you know you want to have cold drinks ready, then you usually bring in an ice box, and an ice box is designed to act as an almost isolated system so that the cold drinks stay cold despite, you know, the summer heat. So a thermos, an ice box, those are both examples of what I would call pseudo-isolated systems. Very good insulation, but not quite the same as isolation, though it does kind of give you the general idea of what an isolated system is. Okay, so those are all the different types of systems. Again, most chemistry teachers don't really bother talking about this, but I think it is important. So, yeah, in chemistry, usually our system is going to be the substances that are being reacted and being formed. And if you're also doing physics at the same time that you're studying chemistry, then you might do thermal physics, which is kind of similar to thermochemistry. There's a lot of overlap between chemistry and physics when it comes to this topic in particular. So in physics, you might actually use the opposite. So in chemistry, you use like the chemicals as your system, while the stuff that your chemicals are swimming in, usually water, will be considered the surroundings. But in physics, it's the opposite. You'll usually have like the water as the system, while the reacting chemicals that heat up or cool down the water will be your surroundings. So that's a little note for those of you that are taking physics. Okay, so now we've covered all the different types of systems. Let's get to talking about some of the state functions that are relevant in chemistry. So first we've got the concept of internal energy, the internal energy of a system. So internal energy, in chemistry it's usually represented with a capital E. In physics it's often represented with a capital U. Don't ask me why. Internal energy, in chemistry we represent it with a capital E, is the sum, it's defined as the total of all potential and kinetic energies, potential and kinetic energies of the contents or components of a system, of the components of a system. So if my system is, say, a box full of gas particles, then the total of the kinetic energies of the gas particles that are allowing them to move, plus the potential energies, if they're bonded in any way, there's some potential energy stored in the form of electric potential energy keeping their bonds. The sum of all of those energies, that's what's called the internal energy or total energy of the system. You probably care more about it if you've studied potential and kinetic energy in physics. You probably won't care too much about this definition if you're purely studying chemistry. But that's what internal energy is. And the change in internal energy, delta E, whenever you see that triangle symbol, the delta, that means change in something. So the change in energy, the change in internal energy, in chemistry we say it's Q minus W. In physics it's Q plus W. But it all depends on how you define these two things. So what are these two things? What on earth is Q? What on earth is W? Q is the heat. Q is the change in heat. W, on the other hand, is work. Those are the only two forms of energy change for a system. The only way that the energy of a system changes is if it gains or loses heat, or if it has work done on it or work done by it. So, of course, if a system absorbs heat, if heat goes into the system from the surroundings, then Q is going to be positive. If heat goes from the system to the surroundings, then the value of Q is going to be negative. So if I made some tea, then while I'm warming up my tea, you could say that if I consider, my teapot with the water in it, or my coffee pot rather, with the water in it to be my system and nothing else, so the stove is part of the surroundings, then heat is coming from the stove to my water in the teapot or coffee pot. I'm going to be tripping over my words all day long if I keep on talking about this coffee pot. I probably should have used a different example. Anyway, if I consider the contents of my coffee pot to be my system and the stove to be part of my surroundings, then of course while the stove is on, heat is going from the stove to the coffee pot, so from the system to the surroundings. So in that case, Q would be positive. My system, the part of the world or the part of the universe I'm concerned with, is gaining heat from the part I'm not so concerned with. And after I make my tea and I let it sit on the counter for a while to cool down, that's where it's losing heat to the surroundings. It's losing heat to the surrounding air, amongst other things. So in that case, I would have a negative value for Q over here. As for work, those of you who've done your physics, you already know what the concept of work is, but for those of you who haven't, we're going to need an illustration to help clarify what work is. So I'm going to attempt to draw this thing right here, but I'm not that good of an artist, so we'll see how it goes. But now you know what it is I'm trying to draw, so maybe that'll make up for my lack of artistic skill. I'll try my best, though. So suppose we have a container. Let's make it cylindrical. And let's say over here is like where you've got your sort of lid or cover. So this is going to be like a disc-shaped sort of plug or lid or cap or whatever you want to call it. So this thing is known as a piston. And in here, let's say you've got some gas. Let's say you've got some gas particles just scattered within here. And of course they have a certain volume. And let's suppose, you know, this lid obviously has some sort of weight to it, but let's pretend that it is weightless and instead replace it with, say, a block that we put on top of the lid. And that'll basically be generating all the downward force pushing down on the gas and keeping it in the container. So if I have just dropped this block onto the top of this lid, onto the top of the piston, then what I'm going to expect, what I expect to see, is that the height of this piston will start to go down. The gas will get squeezed by this, by the force created by this external object, this external weight. So in that case, we would say that this block, with its weight, with the force of its weight, has done work on the gas particles. It has squeezed them, it has pushed them through some sort of distance, it has done work on them, it has given energy to them. When you squeeze them closer together, you're basically giving them energy, because if you think about it, you're reducing the volume, you're probably going to have some of the gas particles, while you're reducing the volume, will be in contact with the piston, and so they'll kind of get a push, they'll get a bump, they'll get a boost to their kinetic energy, for example. On the other hand, let's say I still have this block here, and the gas got compressed, and then later maybe I add some heat. I light a fire under this container, and the gas particles in there, they gain some energy, and they eventually gain so much energy that they start pushing the piston back up. Well, in that case, we would say that the gas, which I consider to be the system here, did work on the surroundings, did work against the weight of this block. So if you push on the system, you do work on the system, then you're if you do work on the system, then you're adding energy to it, and if you let the system do work on the surroundings, then energy is being lost. And I just realized I used the wrong sign convention here. I'm thinking in physics mode. This should be a plus W. This should be a plus W. It's minus W in physics. In chemistry, it's plus W because of how we define work. So in chemistry, positive work is done when it's work done on the system. So if it's the block that pushes the gas down and squeezes it, then I would plug in a positive value for work here. On the other hand, if it's the gas that actually expands and pushes the block back upward, then the system is doing work on the surroundings, in which case I would plug in the work as a negative. In physics, they make it minus W, and then they say that it's work done by the system that's positive, while work done on the system is negative. So in the end, it's the same thing, as long as you keep track of where the energy is going to and where it's coming from. But in chemistry, work is considered positive when work is done on the system, and negative when it's done by the system. In physics, it's the reverse, but if you're not doing physics, then don't worry about that. Let's see, what else did I want to say? Right, so the work, there's actually a formula for it, which anybody who's done physics already is familiar with. Work is equal to, and I'm oversimplifying it here, but it's equal to the force applied times the distance that is achieved when doing that work. And I can already hear the physics students complaining in the comments that it's actually the dot product of force and displacement, and I should have a cosine in there, but we're not doing physics, we're doing chemistry. So, oversimplified, but work for our purposes is just force times distance. And force, you might recall from the last video, is equal to pressure times area, because in the last video we said that pressure is equal to force divided by area. So if I multiply by area on both sides, pressure times area equals force. So those two equations are interchangeable. So yeah, force is pressure times area. So basically, if I can figure out how much force this block exerts downward, I can figure out what the external pressure on the system is. If I can figure out the weight of this block and the area of this disk, the cross-sectional area of the disk, then I can divide the two and I can determine what's called the external pressure. There is also the internal pressure of the gas. We're not going to worry about that because it's not very reliable for our calculations. The problem with using the internal pressure is that it'll be changing as the volume of the gas changes, and if you're working with a changing pressure to calculate work being done, then you're going to need calculus, and in chemistry, at least in general chemistry, we do not use calculus, though we probably should. Anyway, so let's see. Lost my train of thought. Oh goodness, where was I? So force is pressure times area. And yeah, if we know the external pressure and we know the area, then we can calculate the force. And if we multiply that by the distance, so let's say that I squeeze the gas and actually decrease its volume. So there's a distance here. So the piston travels from up here to somewhere around here. And there's a reduction in volume. Well, it turns out that if I want to calculate the work, which is force times distance, force is pressure times area. So work is equal to pressure times area times distance. So I went from force times distance to pressure times area times distance. But what happens when I multiply this cross-sectional area by this distance? Well, this distance, you can think of it as the height. And if I multiply the area of the cross-section by the height, what do I get? Basically, I get the volume of this shaded region. If I multiply the area and the distance, then I get the volume of that shaded region. So area times distance, if I group these together, these are equal to volume. So work is equal to pressure, the external pressure, times the volume, or more specifically, not the volume itself, but rather the change in volume. In this case, the amount of decrease in volume. If it were expanding upward, it would be the amount of increase in volume. So it's pressure times the change in volume, delta V. There's that delta symbol again. Whenever you see the delta in front of anything, then that means the final value minus the starting value. I'm sure some of you are already familiar with that, but for those who haven't seen it before, that's what delta means. The final value of that variable minus the initial value of that variable. It's the change in whatever comes after the delta. So external pressure times change in volume is equal to the work. Kind of. Except we need to make sure that when the volume of the system decreases, work is being done on the system in this case, right? If I'm squeezing the gas down, then I'm doing work on it. I'm giving it energy from the outside because something from the outside is pushing on it. So in that case, the change in volume is going to be negative. If I take the volume after, which is the smaller volume, minus the volume before it got squeezed, then I'm going to get a negative number here. And then my pressure times my negative volume change is going to result in negative work. But we already defined work to be positive if work is done on the system. So in fact, to fix this, what we really need to do is tack on a negative sign right here. And I guess that would also go there. So yeah, work for chemistry purposes is going to be negative pressure external times change in volume. For the physically concerned students out there, I did talk about internal pressure versus external pressure a little bit a couple minutes ago, but let's talk about it again. So, why can we not use the internal pressure? Couldn't we just use pressure internal times change in volume instead? Wouldn't it be the same thing? Well, yes and no. If you assume the internal pressure is constant, then it won't be the same value. It will not be the same value if you just measure the internal pressure before the volume starts changing and don't measure it during the volume change. If you've got a changing volume, then according to our gas laws, you will probably also have a changing pressure, and you can't just, take the initial pressure before volume change and treat that as if it's going to be the same pressure the whole time that the volume is changing. You would need calculus to really determine what the work is if you're using internal pressure. But the external pressure, on the other hand, is going to be constant because the external pressure is due to an external force, and the weight of this block is going to be constant unless, you're inside of some accelerating elevator maybe, or you're quickly warping to different planets with different gravitational pulls, but both of those scenarios sound very unlikely, if not impossible, so I think we're good saying that the external pressure is going to be pretty much constant. So that's why we use it. Okay, so work is negative pressure external times delta V. I'm just going to call it pressure from here on out. In almost every chemistry problem you see, when they talk about the pressure, they are referring to the external pressure, so we don't have to worry too much about internal versus external. Just for those who really wanted to deepen their understanding, there you go. We've covered it, we've talked about it. Let's see, so if I modify my equation over there, delta E would then be equal to Q plus the work is negative P delta V. So then change in internal energy is equal to Q minus P delta V. You're still going to want to remember it in this form because sometimes they will give you really easy, straightforward internal energy problems to do. In fact, maybe we should look at one or two right now before we move on to our next subtopic. Let me see. So this is from my book. It says, calculate delta E and determine whether the process is endothermic or exothermic. Let's talk about that for a minute. Endothermic versus exothermic. Endothermic An endothermic process is one in which the heat energy of the system increases. So in other words, when Q is positive, or Q is greater than 0 in other words. An exothermic process is one in which heat goes from the system to the surroundings. So the exact opposite when Q is negative, when Q is less than 0. So that's endothermic versus exothermic. Anyway, back to the problem. It says calculate delta E and determine whether the process is endothermic or exothermic for the following cases. Part A says a system absorbs 105 kilojoules of heat. So absorbs 105 kilojoules of heat. And does 29 kilojoules of work on the surroundings. Does 29 kilojoules of work on the surroundings. What is the change in internal energy, and is it exothermic or endothermic? You can answer that second question right away because the system absorbs heat. If the system absorbs heat, then Q is positive. Q equals positive 105 kilojoules, which means that this is an endothermic process. Endothermic. The system gains heat energy from the surroundings. Okay. As for the other part, it does 29 kilojoules of work on the surroundings. That means the work is negative 29 kilojoules. The system pushed against the surroundings. It transferred energy to the surroundings in the form of work. Okay, then the total change in internal energy would be Q plus W equals 105 minus 29 equals, what's 105 minus 29? Subtract 30, that would be 75, and then give one back, that's 76. 76 kilojoules. So overall, the system gained 76 kilojoules worth of energy. Oh, I just realized there was something I forgot to do back on this past slide. I guess you could call it a slide. Past sheet, I should say. Which is proving that pressure times volume actually gives you energy units. I mean, it's kind of proven already, if you're willing to trust the physics, that force times distance does give you work, which is measured in units of energy, and we proved that pressure times area is force. So pressure times area times distance should still be the same as force times distance, but let's look at the units and just be extra sure that we do indeed get joules or kilojoules or whatever energy units you want to use. So pressure, as you may recall in the previous video, is typically measured in, well, we measure it in all sorts of units, pascals and psi's and atmospheres and millimeters mercury, or torricellis if you prefer, or kilopascals or bars or whatever. But the standard unit for pressure is the pascal, and a pascal, 1 pascal, is equal to 1 Newton, that's the unit of force, per square meter, the unit of area. And I believe I showed in the previous video, when converting to one of the different versions of the gas constant, that when you multiply pascals, units of pressure, by cubic meters, units of volume, then you get Newton meters, which are the same as a joule, and joules are units of energy. So let's see, pascals times cubic meters, pascals times cubic meters would be newtons per meter squared times cubic meters. And of course, cubic meters divided by meters squared is just meters to the 1, so that's equal to Newton meters which is the definition of a joule, which is a unit of energy. So just in case you forgot when we did it with with the gas constant in the last video, or if you skipped that part of the last video, there it is again. So yes, pressure units times volume units do give you energy units. Sometimes we might have to deal with the pressure being in atmospheres and the volume being in liters. In that case, we need to know how to convert to units of joules or kilojoules, because those are the standard energy units. So how would we do that? If I have pressure in atmospheres and volume in liters, then the units, when I multiply them, when I multiply pressure and volume, will be liter atmospheres, or atmosphere liters if you prefer. And I need to know how many joules this is. How many joules are in 1 liter atmosphere? I hope you remember your conversions from the previous video. So I know that 1 atmosphere is equal to 1.01325 times 10 to the 5 pascals, and I can barely fit that in there. So that cancels atmospheres and gives me pascals, and then liters. A liter is a cubic deciliter, and a cubic meter is 1,000 cubic deciliters. So I can say every 1,000 liters is equal to 1 cubic meter. If you're not sure why this makes sense, go back and see whichever part of the previous video in which I converted liters to cubic deciliters, and then, cubic decimeters, and then cubic decimeters to cubic meters. Or maybe it would be faster to just kind of Google the conversion, whichever you're more comfortable with. But yeah. Let me see. So if I divide by 1,000 here, that reduces with 10 to the 5, making it 10 to the 2. And then 1.01325 times 10 to the 2 would give me 101.325. And yeah, canceled atmospheres, canceled liters, got pascals times cubic meters, which we just proved are equal to joules. So 1 liter atmosphere is equal to 101.325 joules. Usually I'll just use 101.3, but it is important to remember this. 1 liter atmosphere is not equal to 1 joule, nor is it equal to 1 kilojoule. In fact, it's equal to a little more than 1/10 of a kilojoule. So 101.325 joules, or 0.10135 joules. Usually I will just use 4 sig figs from that number. But there you go, remember that. Now then, do I really want to go over some more problems like this? I think we've got the gist of it. I mean, it's pretty simple, straightforward. So yeah, I think I'm going to skip on that and start talking about constant pressure versus constant volume operations. So when we do reactions and we measure the change in internal energy after doing a certain reaction, we will have two different ways to measure the change in heat. So there's change in heat under constant pressure, and there's change in heat under constant volume. If you keep the volume constant, so if you do a reaction inside of a rigid container, a rigid sealed container doesn't allow any gas to escape, but also doesn't allow the gas to expand or compress, then in that case that's a constant volume operation, and whatever change in heat you measure during that constant volume operation is only going to be heat. So, or I should say, whatever change in internal energy you measure is only going to be change in heat, because if you also add in the work, there is no work. If we subtract P delta V, under constant volume, the change in volume is 0. The volume before equals the volume after. So volume after minus volume before equals 0. If the volume doesn't change, this goes to 0. The heat under constant volume, the change in heat under constant volume, is equal to all of the internal energy change. Is equal to, did I spell that right? Yes. Is equal to all of the internal energy change. On the other hand, if you do a process under constant pressure, which is going to be the more common case, constant external pressure, of course. Think of, for example, if I just do a reaction in a beaker in the lab and maybe some gas bubbles out of there, but the pressure that's being exerted on my open beaker is just the atmospheric pressure, which is pretty much constant. So under those constant pressure circumstances, which are going to be the most common circumstances you'll have in the lab, then the change in internal energy is, of course, the heat under constant pressure plus the work, which is equal to negative P delta V. So once you have a constant pressure and you do allow a volume change, then of course P delta V is not necessarily going to be 0. You might say, well, if I do a reaction in an open beaker, I don't really see a volume change, and yeah, you're right, you don't see a volume change if you do it with an open beaker, but if you were to put, say, a balloon or something made of rubber and put it on top of the beaker, cover up the beaker with something elastic and stretchy, then you did the reaction and the reaction formed a gas, then that balloon or whatever elastic cover you put on your beaker, you would see its volume expanding. You would see its volume expanding. The reason you don't see it when there is no plastic, flexible, I shouldn't say plastic, but elastic cover on the beaker, the reason you don't see a volume change when you don't have that elastic lid is because, well, it's basically changing the volume of the atmosphere, if anything, and the atmosphere is so big that if its volume did change by introduction of more gas, then you wouldn't notice a change, especially when the gas is clear and invisible. Actually, I don't know if the volume would change at all. I think the gas particles would just kind of scatter within the gaps that already exist between the gas particles that are already in the atmosphere. Okay, I might be overcomplicating things here, but it's food for thought. But yeah, if you want to see the volume change under those circumstances, then definitely use something like a plastic cover or elastic cover to do that. Also, there's, let me see if I can dig it up. I think I saw an illustration in my book earlier when getting ready for this. Where did it go? Ah, yes, here it is. So there's actually this setup right here where they do a reaction between zinc and hydrochloric acid, which of course produces hydrogen gas, and they do it in a closed container where the container is attached to a piston, a small little tube with a piston in it. And of course, once the reaction is done and some hydrogen gas bubbles out, then the piston gets pushed upward by that extra gas that was introduced. So yes, gas-forming reactions can cause a volume change. They could cause a volume increase or a volume decrease depending on how hard the gas pushes versus the atmosphere pushing down on it. But yeah, there is a way to get this volume change, but usually we're not going to concern ourselves with doing that. Usually in the lab we're not going to get a balloon and put it on the cover of our beaker to measure the volume change. Usually we're just going to leave this out and just focus on the heat part of it. So let me write down this definition here. Heat under constant pressure. Usually, when we do experiments in the lab, we're just going to focus on measuring the heat under constant pressure, and we're not going to focus on the change in internal energy. Instead, we're going to focus on this new concept called the change in enthalpy. Delta H, which is the change in enthalpy, is defined as the change in internal energy minus the work. The change in internal energy without the work. So in other words, it's equal to change in energy plus P delta V. And what's change in energy plus P delta V? Well, if I add P delta V to both sides of that equation, if I add P delta V here, and I add P delta V here, then what I would get, I would basically cancel out the P delta V on the left-hand side, and all I'd be left with is QP. So in other words, delta H is simply equal to QP, just the heat, without the work. So how does QP compare with QV? Well, it turns out that for most reactions, QP and QV, though different, are very, very nearly equal in most circumstances. In most circumstances, QP and QV are very nearly equal, but of course they are not necessarily equal. Delta H, the change in enthalpy, is the heat under constant pressure when you ignore the work done and when the work being done is only pressure volume work. We haven't talked about other types of work that you could do, but there are other types of work that could be done on a system or by a system, including, for example, electrical work. We will see some of that when we get to the electrochemistry chapter. But yeah, you can actually add energy to a system by running electricity through it, or you can even set up a system in such a way that it produces electricity and gives it to the surroundings. Let's say you hook up some reactants to a light bulb and you can power the light bulb. You could consider the light bulb to be part of the surroundings. But yeah, as long as the only type of work that is possible in your reaction is pressure volume work, then whatever the change in heat is under those constant pressure circumstances, that is the change in enthalpy. Okay. Let me see here. So we've talked about enthalpy, we've talked about constant volume versus constant pressure. What to remember from all this? First of all, let me highlight. So delta E is equal to QV, and delta H is equal to QP. They are not the same thing. So this I would want you to remember. You don't need to remember that delta H is equal to delta E plus P delta V. Just remember that delta H is equal to QP. And yeah, just remember these two. So these two you're going to want to remember, and of course the previous equations. So you are still going to want to remember delta E is Q plus W, and also that W is negative P delta V, and also the definition of endothermic versus exothermic. It's very easy to get confused by all these very similar looking equations. I know they threw me for a loop when I was in high school, and I had to reread that section of the textbook over and over and over again until I finally saw the difference between all the different things. But yeah, let's move on to how this relates to chemical reactions. So now it's time to define the concept of heats of formation. Heat of formation. So all of the heats of reaction that we will be talking about are going to be enthalpies and not changes in internal energy. They're going to be enthalpy changes. So we will be abandoning delta E. We will mostly be working with delta H values, both in this chapter and in future chapters. This is not going to be the end of delta H, but this is pretty much the only chapter where we concern ourselves with delta E. So heat of formation. What is heat of formation? It is defined as the change in heat, let's call it QP, or delta H in other words, associated with the formation of exactly 1 mole of a compound from its pure, naturally occurring forms of its component elements. And yes, that is a mouthful, but those words are very, very important. It's not just a bunch of technical mumbo-jumbo for the sake of being technical mumbo-jumbo. So let's go through this whole definition and what it means. It's probably best to illustrate it with an example. So let me move on to another page. Can you see all of that? Yes, you can. Okay. I know I shift the papers a bit when I write, so I have to constantly double check and make sure they're within your field of view. But let's say that I wanted to form water. Let's say I wanted to form water from hydrogen gas and oxygen gas to form H2O. Okay, so hydrogen gas, of course, it's a pure element, so we've got that part taken care of. So pure, naturally occurring forms of its component elements. What does naturally occurring form mean? That means the form in which it exists in nature. So if I was talking about carbon, for example, maybe I should do that one too. Carbon plus oxygen gives me carbon dioxide. If I was talking about carbon, the naturally occurring form of carbon is graphite. the stuff in your pencil lead. I don't know if you can see that very clearly, but that's graphite. Diamond is also pure carbon, but diamonds are not the quote-unquote naturally occurring form of carbon. At least they're not the most abundant naturally occurring form of carbon. I know some people will argue that, well, it is naturally occurring because you know, diamonds are formed in nature, but that's not what is really meant by naturally occurring. What they mean by naturally occurring is, you know, in its like rawest form, before any sort of process is done to it, before any sort of pressure or heat or anything is applied to it. The problem with diamonds is that diamonds are what you get when you apply lots of heat and pressure on graphite or other raw forms of carbon. So diamond technically has energy stored in it because of all the energy it took to create the diamonds, which is going to be important in a minute when I define what the heat of formation is for a naturally occurring form of a raw element. But anyway, for hydrogen, its naturally occurring form is as a gas, right? At room temperature, it's a gas. Oxygen is also a gas at room temperature. That's its natural form when it's a raw element. Water, on the other hand, you could form water vapor or you could form liquid water. In this case, let's say that I want the heat of formation for liquid water. So they said it's the heat change or enthalpy change associated with the formation of exactly 1 mole of a compound from its pure, naturally occurring forms of its component elements. So if I want to get exactly 1 mole of liquid water to get the heat of formation of liquid water, then I have to balance this equation differently from what we've been doing before. In this case, I don't balance it the way I normally do. Normally, we would balance this by writing a 2 in front of the hydrogen gas and then a 2 in front of the water. But this time you have to have a 1 over here, because that's how you define the heat of formation. It's the heat associated with forming 1 mole of the compound from however many moles of the pure elements in their quote-unquote naturally occurring forms at room temperature. So in this case, we're actually allowed to use fractional balancing coefficients. 1 mole of hydrogen gas plus half a mole of oxygen gas gives you exactly 1 mole of liquid water. We are allowed to use fractions to balance these types of chemical equations. These are called thermochemical equations. These are called thermochemical equations. Their whole purpose is to simply define the heats of formation for different compounds. So with thermochemical equations, you can use fractional balancing coefficients because, quite frankly, you have to. You have to because of the definition. The definition of heat of formation, it's associated with the formation of exactly 1 mole of the compound. So if this number has to be 1, then sometimes you have to use fractions to force it to be 1. Now then, carbon, oxygen, forming carbon dioxide. So carbon in its naturally occurring form is solid, but oftentimes you're also going to want to write the word graphite to clarify that you are actually using, you know, the rawest form of carbon. And then oxygen will just be a gas, and of course to get 1 mole of carbon dioxide, it's already balanced. You just need 1 of this and 1 of this, and there you go. And carbon dioxide, we're going to want it as a gas, of course. And yeah, there you go. So those are thermochemical equations. Basically, the heat of reaction for these thermochemical equations will be the heat of formation for the compound that is set as the product. So let's talk about heat of reaction in general, and then we'll go back to this and talk about a special property of the raw elemental forms of pure elements. Heat of reaction, not the same thing as heat of formation. Heat of reaction. Now we go back to balancing our chemical equations like normal. Now we go back to balancing chemical equations like normal. So if I want to calculate the heat of reaction for a given reaction, then what I'm going to have to do is use the heats of formation to calculate it. To calculate heat of reaction, to calculate delta H reaction, and we abbreviate the word reaction RXN because that makes perfect sense. Chemists abbreviate everything, remember that. If you look at the periodic table, it's basically a chart of abbreviations. Anyway, the heat of reaction is going to be equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. And we'll make sense of this soon when we get to our example. But yeah, if you're intimidated by the capital sigma symbol, it just means the sum of. You're going to see this in your math class if you haven't seen it already, so it's time to get comfortable with it. It just means the sum of. The capital sigma symbol just means the sum of. And of course there are little things you can write on the bottom and the top that determine like how many things you're adding to get that sum, but generally speaking the sigma symbol just means the sum of and then whatever's after it. So the sum of the heats of formation of all the products multiplied by their balancing coefficients minus the sums of the heats of formation of the reactants multiplied by their balancing coefficients. Let's look at an example. Let me switch that off and switch this on. Okay, so it's telling me to use Appendix G, which is a table of heats of formation, to calculate the standard enthalpy change for each of the following reactions. Enthalpy change is also another word for heat of reaction, or I should say heat of reaction is the enthalpy change of a reaction. And as for the word standard, that just means under standard conditions. So in thermochemistry, that would mean at room temperature and at normal atmospheric pressure of 1 atm. Anyway, first we have, I don't want to do A or B because those are, yeah, don't want to do those. Let's do C. So we've got Fe2O3 solid plus 3H2 gas. Actually, no, I don't want that one either. Okay, let's do D. Because all the other ones contain raw elements, and I don't want to talk about those just yet. So 2LiOH, let me copy it down. 2 lithium hydroxide plus carbon dioxide. And lithium hydroxide is solid in this case. Carbon dioxide is a gas. Yes, in this case I do want to be careful and actually include the states of matter, because depending on the state of matter, the heat of formation may be different. Lithium carbonate solid. And H2O gas. H2O gas. Alright, I've copied that down. So now let's go ahead and look at our table of values. So let's see, what do I want to look up first? I imagine I'll run into the carbons and hydrogens earlier than the lithiums, but let's just go through this chart. Let's see. Yeah, I think it's in alphabetical order. So carbon, there we go. We've got carbon dioxide gas, which has an enthalpy of negative 393.51 for its formation. So I'm going to write that down for carbon dioxide, negative 393.51. And I think that was in kilojoules per mole. Yeah, it's in kilojoules per mole. Okay, next up we've got... Is lithium carbonate going to be included here? I doubt it. Yeah, it's probably listed under lithium. Water, and then I guess the lithium compounds. Let's see, hydrogen, where? Oh, where is hydrogen? There we go. Water, in this case we want water in the vapor form, so that's negative 241.82. Liquid water has a heat of formation of negative 285.83. So negative 241.82 for water as a gas, negative 241.82. I think I should zoom in on this, would be better. Yeah, there we go. That's probably easier for everybody to read, including myself. And now we go to lithium. Lithium. There we go. So lithium hydroxide solid, negative 487.5. Kilojoules per mole. And then lithium carbonate, also solid, negative 1216.04. Now, some of you might be wondering, what about all those other numbers in the other columns? Those numbers will matter when we get to the thermodynamics chapter, which is a second semester topic, so it'll be a while before we get there. Thermodynamics is going to be one of the last chapters we cover. So, yeah, don't worry about those other numbers until then. They'll become relevant later. But yeah, that should be everything from there. So let me go ahead and switch back to here. And let me see what I've got. So those are the heats of formation in kilojoules per mole. So it matters how many moles are being reacted and how many moles are being produced for the reactants and products. This equation is already balanced for us. Everything has a balancing coefficient of 1 except for the solid lithium hydroxide. So for the solid lithium hydroxide, since I've got 2 moles of it, based on my balancing coefficient, 2 moles of lithium hydroxide for every 1 mole of carbon dioxide and 1 mole of all the other stuff, then I would have to multiply the negative 487.5 by 2. So then, my heat of reaction, maybe I can fit it in up here. my heat of reaction is going to be equal to, first, the sum of the heats of reactions of the products, energy of products minus energy of reactants. So we've got negative 1216.04 times 1 plus negative 241.82, negative 241.82. So that's the products, minus the sum of the heats of formation of the reactants. So we've got 2 times negative 487.5 for the lithium hydroxide, plus negative 393.51 for the carbon dioxide. Maybe squeezing it into that tiny little corner was a bad idea. But if I put all that into my calculator, and yes, it is very, very, very important that you remember the parentheses around your reactants, especially. With your products, you can get away with not having these parentheses, but for the reactants, remember to include them because that minus sign does distribute. A lot of students will forget that, and they'll subtract the first reactant, but not the second one. And of course you'll make a calculator mistake there, you'll get the wrong number, and you'll be confused as to what you did wrong, and you'll attribute your mistake to everything but a simple error in distributing the negative sign. So remember those parentheses. I know it sounds like a well duh, but lots of people make that mistake. So you have been warned. Practice, practice, practice so that you can get used to catching yourself when you're about to make this mistake. Negative 1216.04 plus negative 241.82, and then minus 2 times negative 487.5, also minus negative 393.51, because remember the minus sign distributes over these. That gives me negative 89.35, but one of the numbers I plugged in had 1 decimal place while the others had 2 decimal places, so according to my rounding rules I should have just 1 decimal place in the end. So negative 89.35 will simplify to negative 89.4, or will round to negative 89.4, and that's going to be kilojoules per mole. Right? Under addition and subtraction, the units don't change, and what I added and subtracted were kilojoules per mole. But now there's an interesting question that arises. Kilojoules per mole of what? Kilojoules per mole of what exactly? Is it per mole of lithium hydroxide or per mole of carbon dioxide? So this is where it gets kind of weird, but if you spend time thinking about it, maybe it'll make more sense after you give it, I don't know, 15 minutes of thought, if it's not very apparent to you already. But basically, this is negative 89.4 kilojoules per run of the reaction, you could say, per mole of reaction. So basically, it's negative 89.4 kilojoules of heat for every 2 moles of lithium hydroxide, but also for every 1 mole of carbon dioxide, but also for every 1 mole of lithium carbonate, but also for every 1 mole of water vapor. So it really depends on what you want to compare it to, but it really depends on which substance you want to calculate from. But basically, if you take the balancing coefficients to represent the number of moles of each of these reactants or products, then this is how many kilojoules is associated with that number of moles of that particular substance. I don't know if that just sounded like a nonsensical word salad to you, or if it made complete and total perfect sense, but maybe later on when we do some calculations with heats of reaction, it'll start to make more sense. Anyway, so now we've looked at an example of how to calculate heat of reaction. You take the energies of the products minus the energies of the reactants, and that kind of makes a lot of sense. The total energy you have after minus the total energy you had before is equal to the change in energy. If your products have more energy than your reactants, then product energy minus reactant energy equals the total energy gained. If your products have less energy than your reactants, then when you do products minus reactants, you'll get a negative, and that will tell you how much energy was lost. In this case, overall, we got a negative number, so that means our system lost energy. What is our system? Our system is these atoms. The lithium atoms, the oxygen atoms, the hydrogen atoms, the carbon atoms. Those are the system. When they were bonded in these compounds, they had a certain amount of potential energy, and when you broke those bonds and formed new bonds, they had even less energy. So energy went in to break these bonds, and when new bonds were made, well, that's the reverse of making bonds. So if it takes energy to break bonds, then making bonds must produce energy. And it turned out that the energy that was produced, the energy that was released, was greater than the energy it took to break apart these atoms in the first place. So overall, these atoms lost energy, which means they give off heat. They lost energy to the surroundings, so if you did this reaction in, say, a beaker or some other container, then you would notice the container warming up, because the container would be the immediate surroundings of these atoms. Okay, and actually that helps explain where we get heats of formation from. So let me show you this diagram. So in fact, if you want to calculate heats of formation, all you have to do is do the reactions of the raw, naturally occurring forms of pure elements to make compounds. And if you do it in a setup like what you see on the screen, then you will be able to determine the heats of formation for all these different compounds. Of course, you're going to need to measure out the amounts of reactants and products you're getting so that you can figure out how much heat exactly you get for 1 mole of the formed compound. But if we look at the diagram, so for an exothermic process, like the one we just did, a negative delta H value or a negative Q value, the heat is going from the atoms overall to the surroundings, and sometimes the surroundings will be a solution if you do the reaction with substances dissolved in water. Other times you might not be able to dissolve things in water, so you might need a different solvent, or you might need a different process altogether that doesn't involve solutions at all. But that's a problem for the people at Dow and NASA and other companies that do chemical reactions to worry about. That's not for us to worry about. For us, all we need to know is there is a process. No matter what compound it is, there is a process that we can use to determine the heat of formation. And this basically explains how we go about doing it. We react our atoms within some sort of surrounding environment and measure the change of the surrounding environment, and then from that work backwards to determine what happened with the atoms. So if the surrounding environment heats up, then that must mean that the system lost heat. If the surrounding environment cools down, then that must mean the system absorbed heat from the surroundings. And yeah, that's the basic setup for measuring enthalpy changes for reactions that form compounds from pure elements, but also for just regular reactions overall, even the ones that are not necessarily for calculating heat of formation. So for this to be useful, for something like that to be useful, you need to be able to use this equation, but that would mean you need to know the heats of formation for the reactants in order to get the heat of formation of the product. If I wanted to do this reaction, this first one that I wrote down, if I wanted to do this in the lab because I didn't have a convenient table or chart made by someone else already, and I didn't know what the heat of formation of liquid water was, but I also didn't know the heat of formation for hydrogen gas and oxygen gas, well, that's a bit of a problem. How do you measure the heat of formation if you have to take the heat of products minus the heat of reactants? If you want to get the heat of formation for one substance at a time, how do you do that if, say, you were the first chemist to record thermochemical data and you didn't know beforehand any of the compounds' heats of formations, or any of the elements' heats of formations for that matter? Well, what they decided to do was just set the heats of formation of naturally occurring forms of raw elements to 0. They just said, you know what, they already exist in nature, they're raw, you don't need to use energy in order to make them, you get them for free, so let's just assume they have a heat of formation of 0. Let's just assign a heat of formation of 0 to these raw elements. Can they get away with doing that? Well, before I answer that question, let's see how this helps us. If I assume that these are 0, and if I'm the first chemist to ever record thermochemical data, then I can do this process now, and I can say the heat of water, the product, minus the heat of hydrogen and oxygen, which I now know because I make them 0, is just equal to the heat of water. So I can measure the heat of reaction using something like what you saw in the diagram I had up a couple minutes ago. And you can attribute all of that heat change to just the product, because you've already set the reactants to 0. So that solves one problem, but does it create another problem? Does assuming that, or not assuming, but assigning a value of 0 to these create any problems? Well, no, not really. And the reason it doesn't cause any problems is because we don't really care how much energy all these substances have per se. What we care about is how much the energy changes. What we care about is the delta H. We don't care about the H itself. We care about the change in energy. So if we set these to 0, that's fine, because we're just basically setting our benchmark. You have to set something equal to 0 when the only thing you care about is the difference between two things. If we let our raw elements be like our reference point and set them to 0, then we get the same delta H that we would have gotten if we set them to any other number. Because if I were to set hydrogen and oxygen to, let's say, 100 kilojoules each, then that would just mean that the heat of formation of water would also be 100 kilojoules higher than what I would have gotten if... Wait, did I say that right? No. So, let's say, and I'm just making up numbers here, let's say, and I'll do this in peach, let's say, for example, that the energy of this was 100 kilojoules per mole, and for oxygen it was let's make it 200 kilojoules per mole because of that 1/2. And let's say the H2O liquid was, oh, I don't know, let's say 300 kilojoules per mole. Let's say this wasn't the change in enthalpy for each of them, but this was the actual, like, absolute enthalpy for each substance. And I know I'm going into a tangential topic here, but I know some people want to know about this, so I'm covering it. Then in that case, I could do this process, so I could do 300 minus 100 and also minus half of 200. And then I would be left with a total of 100. I would be left with a delta H is equal to 100 kilojoules per mole. The fact of the matter is, the product has 100 kilojoules per mole more than the reactants did. Now, what if I set the reactants to 0? Well, if I set both of these to 0, since the product has 100 kilojoules per mole more than the reactants do, it's just going to have 100 kilojoules per mole more than the reactants. It's just going to be 100 kilojoules per mole. So the delta H here would still be 100, because I would do 100 times 1 minus 0 and also minus a half times 0. The delta H would once again still be 100. So it doesn't matter what you set these to. You just had to pick something, because what we really care about, we don't care about what the actual H values are. We care about the difference in H between liquid water and these elements. So by setting the elements to 0, that would be the most convenient for us. It would make the math simpler. And of course, I know when we look up water later, its delta H of formation is not even going to be 100, because I don't think any substance has a heat of formation that's such a perfect number. But, you know, I was just making those numbers up for the sake of an example. So don't take those too literally. Where do I want to go from here? Let me think. I think now we're good to go with some more problems. Remember, the heat of formation for a raw element is set to 0. Later on, you might encounter problems where they give you all the heats of formation except for one, and you'll think that you're missing information and that the teacher made a mistake writing the problem, and you'll probably be wrong. It'll probably just be the case that the substance whose thermochemical data is missing is a raw element whose heat of formation is 0. Anyway, let's take a look at some of the ones we skipped. So I've got part A for problem 68 says we've got nitrogen gas plus oxygen gas gives us 2 nitrogen monoxide gas. Well, this is kind of interesting. So they want us to get the heat of reaction for this, but you might notice something about this. Let me switch back to my camera and copy this down. So N2 gas plus O2 gas gives us 2 NO gas, and we want the heat of reaction for this. Okay, so if I were to multiply this whole equation by 1/2, what would I have? What would I end up with? I'd end up with the thermochemical equation for the formation of nitrogen monoxide. 1/2 nitrogen gas plus 1/2 oxygen gas gives us 1 nitrogen monoxide gas. The delta H reaction for this particular reaction would also be equal to the heat of formation of nitrogen monoxide. So delta H for this process, which is heat of formation of nitrogen monoxide minus 0 and minus another 0, would be heat of formation of nitrogen monoxide. How shocking. But if you realize this, then you will realize immediately that the delta H reaction for what I have up here is simply 2 times the heat of formation of nitrogen monoxide. So let's look to our table of thermochemical data, and let's see where nitrogen monoxide would be. Nitrogen is right there. Nitrogen monoxide, 90.25. 90.25, so that's for every 1 mole of nitrogen monoxide is 90.25 kilojoules, and that's positive. So if I switch back to my camera, let's see. Then all I have to do is 2 times 90.25 minus, well, 0 and 0. So 2 times 90.25 is equal to 180.50. 180.50 kilojoules or kilojoules per mole. So sometimes you'll see answers written in just kilojoules for delta H reaction, and that's fine, but know that it's implied that it's kilojoules per mole and not necessarily per 1 mole. Like we said earlier, in this case it would be kilojoules for every 1 mole of nitrogen reacting with 1 mole of oxygen to form 2 moles of nitrogen monoxide. So if I were to ask you the question of how many kilojoules of heat are needed to form 1.7 moles of nitrogen monoxide, then what you would do is you would say, well, 1.7 moles of nitrogen monoxide for every 2 moles of nitrogen monoxide, it requires 180.50 kilojoules of heat. And then you'd just calculate how much heat that is. On the other hand, if they told you it was 1.7 moles of oxygen, then I would do 1.7 moles of oxygen times, we get 180.50 kilojoules for every 1 mole of oxygen in the reaction. So keep that in mind. You can think of delta H reaction as either being a reactant or a product if you want. In this case, delta H reaction was positive, so this was an endothermic process. Right? Positive delta H is a positive QP. Positive Q, we said, was for an endothermic process. So in this case, the heat required to break the bonds within nitrogen and oxygen was greater than the heat that released when you made bonds to form nitrogen monoxide. So it required more heat going in than the amount of heat going out. Overall, you could write 180.50 kilojoules of heat. You could think of it as a reactant in this case since it goes in. If it were negative, you could list it over here at the end like a product since it's coming out. But I digress. Let's look at another one. So, let's see. B is actually simple, straightforward, because, and I'm looking still at problem 68, because you've got solid silicon, well, that's the natural form of silicon, and chlorine gas. Chlorine is naturally a gas. So those are pure elements in their natural form. And then you've got a compound. It doesn't matter for a compound whether it's in its natural form or not. Compounds do not have 0 for their heats of formation. But if you look at this equation, then that's basically just a thermochemical equation for defining the heat of formation for silicon tetrachloride gas, for defining its heat of formation. So all I'd have to do for this one is just look it up in the table and I'm done. All I'd have to do is look it up in the table and I'd be done. So we'll skip that one. Part C, we've got Fe2O3 plus 3H2 gives us 2Fe plus 3H2O. Okay, that one looks interesting enough. Let me see. Any interesting ones among 69 or 70? Because I don't want to spend too much time doing each and every one of these. I just want to pick the most relevant examples. Let's look. We've got... skip that one. Skip that one. Well, actually... yeah, that one's skippable. What about number 70? What's different about this? Determine the enthalpy change under standard state conditions for each. I don't see anything too different there. I mean, A looks interesting under number 70. Okay, let's do 68C and then 70A. So 68C says we've got iron 3 oxide plus 3 hydrogen gas gives us 2 solid iron plus 3 liquid water. Okay, let's copy that down. Let me wall that off. So Fe2O3 solid plus H2 gas, or actually 3 H2 gas, gives us 2 Fe solid plus lots of water, 3 H2O liquid. Okay. Let's go ahead and look up the heats of formation here. We should already recognize immediately that for hydrogen gas and solid iron, those are the naturally occurring forms of those elements, and they are pure elements. They're not part of a compound, so those should be zeros. So I only need to look up water and iron 3 oxide. So if I go to my thermochemical data table, let me see, where would, I think both of them will be back up here when I scroll up. Yes, okay, we found iron. There we go. Iron 3 oxide is negative 824.2. Negative 824.2 kilojoules per mole. And then for liquid water, last time we used water as a gas, but for liquid water, should be under hydrogen. There it is, negative 285.83. Negative 285.83 kilojoules per mole. Okay. Let's go ahead and switch back to our camera. So this shouldn't be too hard to do. If I want to calculate the delta H reaction for this, it should just be 3 times negative 285.83 minus 1 times negative 824.2. And again, these other substances are zeros, so no need to even bother counting them. So if I do that on my calculator, and I see I've got 2 decimals here versus 1 decimal here, so I should round to 1 decimal in the end. So negative 285.83 times 3 minus negative 824.2 is negative 33.29. Negative 33.29. When I round to 1 decimal place, it's negative 33.3 kilojoules, or negative 33.3 kilojoules per mole. And that's per 1 mole of Fe2O3, or per 3 moles of H2, or per 2 moles of Fe, or per 3 moles of H2O. And since it's negative, that means this is an exothermic reaction. You can think of the 33.3 kilojoules per mole as being a product, so you could write plus 33.3 kilojoules right here if you want to think about it that way. But yeah, there we go. So that's that one. Now I wanted to do 70 part A. So that one says we've got 2 solid silver oxide, gives us 4 solid silver plus oxygen gas. So notice with this one, there's something very similar between 70A and 68A. So what I pointed out for 68A is that you may have noticed it was simply 2 times the thermochemical equation for the heat of formation of nitrogen monoxide. Well, 70A is kind of similar, except it's flipped. So it's like a reverse thermochemical equation where the compound is on the left and the raw elements are on the right. So if I write this down, we've got 2Ag2O solid gives us 4Ag solid plus 1 oxygen gas. Well, this is 2 times the reverse of the thermochemical equation for determining the heat of formation for solid silver oxide. So it's basically 2 times this. It should be 2Ag solid plus 1/2 of O2 gas, giving you Ag2O, exactly 1 mole of Ag2O. So if I look up the value in my data table for the heat of formation of silver oxide, then I'm basically going to get the heat of reaction for this reaction down here. And if this reaction up here is basically 2 times the reverse of this reaction, can you guess what it's going to turn out to be? Or how it's going to relate mathematically to the heat of reaction for this green one. If not, that's okay. We're going to get into that soon enough. But let me get to my table. So we have, where is silver oxide? Silver is probably going to be in the S's. Silicon. Okay, so there's silver. Silver oxide. There we go, negative 31.05. So negative 31.05 kilojoules per mole. That's for the formation of silver oxide. Okay, let me switch back to the camera. So now I know it's negative 31.05 kilojoules per mole for Ag2O. So if I just go through the normal process, I would do 4 times 0 plus 0 minus, for reactants, it's 2 times negative 31.05. And 2 times, so minus 2 times negative 31.05 would be positive 62.10 kilojoules per mole. That's your delta H for this reaction. But you might also notice that, one, it's going to be the opposite sign of this green reaction. Delta H for this navy blue, almost black reaction is, first of all, opposite sign, but also twice the value. And this should make intuitive sense to you, especially if you're good with your math, because, yeah, if I flip an equation, then the reactants become products and the products become reactants. If my heat of reaction is calculated from heat of formation of products minus heat of formation of reactants, if I switch their places, if I switch the order of subtraction, then I'm just going to get the negative of the same number. So that's if I just did a flip, right? If I do 5 minus 3, I get 2, but if I reverse the numbers and do 3 minus 5, I get negative 2. So just for flipping the equation, you flip the sign, but also after flipping, so if I flip this green equation and reverse it, that flips the sign, gives me an equation with a delta H of positive 31.05, and then notice that everything in the navy blue equation is going to be 2 times the flipped version of the green equation. So not only do I flip the sign, I also double the amounts of everything, and if you multiply everything in this equation by 2, then you can factor that 2 outside of the whole thing and you get 2 times the whole thing. So yeah, if you double all of the substances in the reaction, then you should double the heat of reaction. This will carry us into Hess's law later when we talk about another method for determining enthalpies of reaction, but let me look at the next set of problems and see if there's anything interesting I want to do there. So we've got 71, decomposition of hydrogen peroxide. And it says determine how much heat is produced by the decomposition of exactly 1 mole of H2O2 under standard conditions. Okay, so basically what we would do there is calculate the heat of that reaction, and then that would give us the kilojoules for every 2 moles of H2O2 decomposed, and then just divide that by 2 and you would get the heat for 1 mole of H2O2. So yeah, we can ignore that one, it's simple enough. 72, calculate the enthalpy of combustion of propane, C3H8, for the formation of H2O gas and CO2 gas. And they gave us the enthalpy of formation of propane to save us some time, that's good. 73 gives us butane, and then 74 says, okay, so let's do 72, 73, and 74. So you see a new phrase there, enthalpy of combustion. What on earth is that? We've talked about heat of formation, or enthalpy of formation, and we've talked about heat of reaction, or enthalpy of reaction. What on earth is enthalpy of combustion? Well, that's just the heat of reaction for combustion reactions. Really, really simple. In fact, there are all sorts of heats of, so to speak. There's heat of combustion, there's heat of neutralization when you neutralize an acid and base together, there's heat of dissolution when you just dissolve something in water. Sometimes dissolving things will generate heat or require heat. That's kind of how, what do you call them, those heat packs and ice packs work. There's like a thing that you break, and when you break it, what you're doing is you're popping out some sort of soluble substance, releasing it from its seal, and letting it get into the water to either warm it up or cool it down, depending on which type of pack you purchased. So if you were wondering how those worked, now you know. But heat of combustion is just the heat of reaction for a combustion reaction. Heat of dissolution is the heat of reaction for, it's not even a reaction really, but the heat of reaction for dissolving something, and so on and so forth. So yeah, whenever you hear heat of, it's just the delta H associated with whatever that process is. Lost my train of thought. Oh, right. Let's do 72. So it says calculate the enthalpy of combustion of propane for the formation of H2O gas and CO2 gas. I still have their heats of formation somewhere. So heat of combustion, so C3H8 is the reactant. And we've got, and that's in the form of a gas, plus oxygen gas for combustion reactions, gives us, in this case it was H2O gas plus CO2 gas. Okay, we're going to need to balance this. So let me see. We have, if I do 3 here and 4 there, that'll be evens. Okay, that'll work. So 3 CO2 and 4 H2O. That would give me 3 times 2 is 6, 4 times 1 is 4, 6 and 4 is 10 oxygens, so I would need 5 there, and we're done. Okay. Now then, copying down the data they gave us in the problem, it's negative 104 kilojoules per mole for the heat of formation of butane, negative 104 kilojoules per mole. For H2O gas and CO2 gas, I know I've used those, so not there. Here, H2O gas, negative 241.82, negative 241.82 kilojoules per mole. And for CO2 gas, it was negative 393.51 negative 393.51 kilojoules per mole. Okay. And oxygen gas, of course, is going to be 0, because we've defined it to be 0 for raw elements. Let's see. So calculating the heat of combustion here, delta H combustion, it's really the same thing as delta H reaction. Delta H combustion is equal to 3 times negative 393.51 plus 4 times negative 241.82, and then minus negative 104. No decimal places, 2 decimal places, 2 decimal places, so I round to no decimal places. Negative 2043.81 gives me negative 2044. Negative 2044 kilojoules per mole. So again, we have an exothermic reaction. Heat is released. Okay, then they wanted for 73, do pretty much the same thing, but now for butane. So it's C4H10. And enthalpy of formation is negative 126. Okay. So for butane, C4H10, and was it also a gas? Yes. C4H10 is also a gas, reacted with oxygen gas, gives us H2O gas and CO2 gas. And for balancing, let's see, if I do a 5 here and a 4 here, that would give me an odd number of oxygen, so a 10 here, and an 8 here, and a 2 here. That should do it. Oh, let me double check the definition of heat of combustion real quick, because I think heat of combustion is supposed to be per mole of the combustible reactant. Let me see, where is heat of combustion mentioned in this book? It's probably in here somewhere. Okay, I can't seem to find it anywhere in there. Let me try and Google it. Gotta make sure I'm using the right definition of heat of combustion, because this could be consequential for the next problem. Google. Heat of combustion. Heat of combustion. Okay, let's see. So heat of combustion. Okay, during the combustion of a specified amount. So it is per mole. Okay, got it. So it's not actually the heat of reaction for a combustion reaction per se. It's going to be the heat of combustion per mole of C4H10, and since I'm using 2 moles here, that would mean I would have to divide that by 2 in the end. Or I could just change this to a 1. Oh, I didn't finish balancing, did I? 10 oxygen plus 16 oxygen is 26 oxygen, so I'd need a 13 here. But anyway, as I was saying, so I could just change this to a 1, change this into 13 halves, change this into 5, and change that to 4. I could do that. Maybe I will. Just preemptively get that out of the way. So 1, 13 halves, 5, and 4. Yeah, because delta H of combustion, so maybe let me write a definition for it. So delta H combustion equals delta H of reaction for a combustible substance divided by the number of moles, the balancing coefficient of that combustible substance, Not an official equation you'll find in a textbook anywhere, but there it is. It's per mole of the substance being set on fire. Okay, now then, with that out of the way, let's just go ahead and calculate like we did before. They gave us negative 126 kilojoules per mole for the butane. So that's its heat of formation. And we already know for water and CO2 we can use the same values that we did before. So I'm going to use these numbers that I have in navy blue. So let's see, we've got 4 for carbon dioxide, 4 times negative 393.51. Uh-oh, what did I do? So 4 times negative 393.51 plus 5 times negative 241.82, and then minus negative 126, just 1 times negative 126, going by the darker numbers, and nothing for oxygen. And that gives me negative 2657.14, which I would need to round to no decimal places. So delta H combustion there is equal to negative 2657 kilojoules per mole of butane. So heat of combustion is specific. Heat of reaction is not specific to any particular substance in the reaction, but heat of combustion is. It's specific to the thing being combusted, which is usually some hydrocarbon compound. Okay, now we've got that out of the way. Let's take a look at what they were asking for problem 74. So it said both propane and butane are used as gaseous fuels. Which compound produces more heat per gram when burned? Okay, so what we're going to need there is the molar masses to convert from moles of C3H8 to grams of C3H8, and same thing for C4H10. So we're going to need to convert from kilojoules per mole to kilojoules per gram to make a comparison. Because yes, it looks like butane has more energy to give off on a per mole basis, but butane is also heavier because it's got 1 carbon and 2 hydrogens more than propane does. So on a gram per gram basis, who wins out? Is it still butane or is it propane? So C3H8, carbon is 12.011 grams per mole, so 3 times that, plus 8 times, for hydrogen it's 1.008, and that's 44.097. So C3H8, 44.097 grams per mole. And then for C4H10, what did I do? C4H10, we've got same things, except now it's 4 carbons and 10 hydrogens. And that's 58.124. 58.124 grams per mole. Okay, and to convert between kilojoules per mole and kilojoules per gram, shouldn't be too hard because I've got my grams per mole. So 2044 kilojoules per mole. For every 1 mole, it's 44.097 grams. That cancels the moles and leaves me with kilojoules over grams. So that's for the butane, or sorry, the propane. For the butane, it's 2657 kilojoules over 1 mole, times for every 1 mole of butane, it's 58.124 grams. And it looks like the yellow marker is on its last legs, which is something I've been looking forward to. Okay, so if I go ahead and calculate those, oh, and of course the moles cancel, we get kilojoules per gram, just confirming that. 2044 divided by 44.097. If I round to, let's see, 4 sig figs versus 5 sig figs, I should have 4 sig figs, so 46.35. 46.35 kilojoules per gram of propane. Must have been a long day for me. And then 2657 divided by 58.124 is 45.71. 45.71 kilojoules per gram of butane. So, in fact, gram per gram, propane is the better fuel if mass is a concern for you. But it's pretty close. So, it doesn't make much of a difference to me, but I guess in very, very large quantities it would eventually spell a difference. If maybe you own some sort of factory that has to choose between burning propane or butane to generate heat for whatever it is you're manufacturing, this could spell all the difference. Especially if the selling price for propane and butane is the same per gram. But what would I know? I don't own a factory. Okay, so that takes care of some basic heat of reaction problems. Now let's take a look at something called Hess's law. Now let's introduce, oh goodness, the fan is interfering with the way this paper's standing. Now let's introduce a little something called Hess's law. So a lot of reactions in the real world happen in multiple steps. You do reaction number 1 to form product number 1, and then product number 1 becomes a reactant in reaction number 2 and forms a second product, and maybe that second product is then reacted with something to form a third product, and maybe that third product is your final product. But yeah, Hess's law applies to equations that happen in a series of steps, and it gives you another way of getting the heats of formation, or rather the heats of reaction for different reactions in terms of already known reactions. So if you have a reaction for which you already know the enthalpy change, you can use it in determining the enthalpy change of another reaction that involves it. So basically what Hess's law says is that if you add two reactions, if you combine two reactions, two or more, if you combine two or more reactions, to create an overall reaction, then delta H reaction for the overall process, actually, you know what, I should use the word processes instead of reactions there, but we'll get to that when we get to that. These rules for calculating heat of reaction and so on, they're not always necessarily for reactions. Sometimes you can do them for a process, such as, for example, liquid water to water vapor. You could do the heat of formation of water vapor minus the heat of formation of liquid water, and that would give you what's called the heat of vaporization, but that's not really a reaction per se. I would just call that a process. You're changing from the liquid state to the gas state, but I digress. Anyway, if you combine two or more reactions to create an overall reaction, then delta H reaction for the overall process is the sum of the delta H values. Why do I keep writing a W? Delta H values for each of the reactions combined, for each of the combined reactions. Okay, what does this mean? Well, it's probably best illustrated with an example, so let's take a look at a simple one for now, and we'll work our way up to a more difficult one. So we've got, calculate the enthalpy change for the following reaction. We've got P4O6 solid plus 2 oxygen gas gives us P4O10. Solid, so that's tetraphosphorus hexoxide and tetraphosphorus decoxide. I'm subtly reminding you not to forget your nomenclature rules there. I hope you appreciate it. Okay, so we are given the following. So we need to find the delta H reaction for this. Delta H reaction equals question mark. And we are given P4 solid plus 3O2 gas gives us P4O6 solid, and we've got P4 solid plus 5 oxygen gas plus 5 oxygen gas gives us P4O10 solid. Maybe drinking water is a more efficient way of clearing my throat than forcing a cough. I really should be doing that more often, but I forget. I'm just so into it. Let's see. So they gave us delta H for this process is negative 1640.1. Negative 1640.1 kilojoules. And delta H for the second process is negative 2940.1 kilojoules. And we need to determine delta H for this process. So is there a way to construct this out of these? And the answer is yes, of course. There is a way to do it. So let's see. There are 3 different things that we are allowed to do for these kinds of problems. Number 1, we can flip an equation and just, change the products to reactants and the reactants to products. If we do that, then we have to flip the sign of delta H. We saw this earlier with the silver oxide example. So you can flip an equation, you can write it backwards, but if you do that, then change the delta H from positive to negative or from negative to positive depending on what it started as. So you can flip an equation. Another thing you can do is you can multiply the entire equation by a constant. So if I wanted to double everything in here, then that's fine, I could do that, but I would also have to double the value of delta H. If I wanted to triple everything here, I'd have to triple the delta H, and so on and so forth. So that's also something that I can do. The third thing that I can do, which we didn't see when talking about the silver oxide example, is I can add 2 equations together. And if I do that, then I just cancel out anything that appears on opposite sides. Kind of like what I did when I showed how to balance redox equations, how we would always cancel the electrons, because we'd always make it so that we have, for example, 10 electrons in the products of one half reaction and 10 electrons in the reactants of the other half reaction, and we'd cancel them out. Also, kind of like when we wrote total ionic equations and we canceled out the spectator ions that showed up on opposite sides of the equation, same thing. So same idea here, we can cancel anything that shows up on both sides when I add 2 equations. But also the other thing when you add two or more equations, when you combine them. You also add their enthalpies. You add their heats of reaction. So those are the three things we can do. We can flip, we can multiply, and if you multiply by a fraction, then that's basically division, so you can multiply and divide, really. And the third thing is you can combine equations. So those are the three things you can do. What do we need to do with these in terms of flipping, multiplying / dividing, and combining in order to get what we have up there? First, what I would do is look at the things that only show up in one place and one place only. So I need to have a P4O6 on the left, and I need to have a P4O10 on the right. If I look at both of these equations in yellow, I see that the only equation that has a P4O6 is this one. So this equation has to be the one to get me a P4O6 on the left, and the way to do that, of course, is to flip this. So I know I have to flip this. It's the only way to get P4O6 on the left. I also know I have to make sure to keep the second yellow equation unflipped, because it's the only place where I have P4O10, and I need P4O10 to come out on the right. So already I know which ones need flipping and which ones don't need flipping. As for multiplication or division, we'll see whether or not we need any of that soon enough. So if I were to flip this, just rewrite it as, I'll just write it up here, P4O6 solid yields P4 solid plus 3 oxygen gas, and then delta H for this, since I flipped it, is the reverse of delta H for the original, so it's positive 1640.1 kilojoules. Okay. Positive 1640.1 kilojoules. Now then, if I look at this green equation and the second yellow equation, which must not be flipped, if I compare those two, let's see, can I combine them directly and get this top equation, or do I need to do some multiplication and or division first? Well, if I go ahead and try combining them right now, I'd get P4O6 on the left, and I would get P4 solid would cancel with P4 solid over here. You know what? Let me just cross out this one so it's not in the way. Yeah, let's cross that one out because it's been distracting me. Okay, so P4O6 on the left, we've got P4 solid on the left would cancel with a P4 solid on the right, 1 and 1. So those would cancel each other out. I've got 3 oxygen on the right and 5 oxygen on the left, so if I cancel out 3 on each side, I'd be left with 2 oxygen on the left, which is exactly what I'm going to need to have. And then the only thing I'd end up with on the right is P4O10. So yeah, we're good to go. This is all we need to do. So if I combine these two reactions, this one in green and this one in yellow, then the P4 cancels out, and 3 of the oxygens cancel out, reducing that to a 2, and you're left with P4O10 there. So just add them directly, no need to multiply anything. 1640.1 plus negative 2940.1 gives us, this one should be easy enough without a calculator, 1300.0. So delta H for the overall process is going to be negative 1300.0 kilojoules. And you could also call it kilojoules per mole, or just keep it as kilojoules. Like I said earlier, either is fine. They tend to write it as just kilojoules in textbooks, but the implication is that it's kilojoules per mole. Okay, so there you go. There's a classic Hess's law problem. Let's do... let me see if the one I have set up in the slide is good enough to practice with. No, those are... Well, let's look at them and see. While I decide, you might as well see what they are in case you want to try them out yourself. Calculate delta H for the process. Mercury 1 chloride decomposing to mercury and chlorine from the information given below. So, for 65, it's pretty simple. Just flip both equations and then add them. Or add both equations and then you'd get the reverse of the equation you wanted and then flip that. Adding the equations doesn't have to be the final step in these kinds of problems. But it's often better strategy-wise to save the addition until the final step, because you do need to flip. If you have to flip one reaction while keeping another reaction the same, then yeah, in that case you definitely cannot add first. So I would say save your addition for last unless you really know what you're doing and you've practiced these enough times that you've got a feel for it. But that's 65, easy enough. 66. That one is already set. Well, no, it's basically the same as 65. Flip them both and then add them and you're done. But what is interesting about this is the compound CO3O4. So that compound, let me think, what would it be called? I know I looked it up the other day because it's my first time seeing a compound like this. It would be called... cobalt 2. Wait. Yeah, it would be called cobalt 2 dicobalt 3 oxide. Cobalt 2 dicobalt 3 oxide. I'm pretty sure that's what the name was. So let's look at that. You probably won't encounter anything like it in your chemistry course. Whether it's at the college level or the high school level, you probably won't come across it, but it piqued my interest, so I looked it up. CO3O4. If you try to go with the reasoning that oxygen is -2, so you've got a total of -8 there, then basically, if you tried to do things normally, you would assume that the cobalt has a charge of 8/3, positive 8/3, which doesn't make any sense. But what does make sense is if you write it like this. If you write it as it's COO and CO2O3. So it's a mix of cobalt 2 oxide and also cobalt 3 oxide. So one of the cobalts has a charge of +2 and two of them have a charge of +3. So I believe this is called, and I could be wrong on this, but I believe it's called cobalt 2 dicobalt 3 dicobalt 3 oxide. Because you've got one cobalt with a charge of 2 and two cobalts with a charge of 3. And then, you know, with the regular oxide ion. So yeah, I found that to be interesting, but other than that, not much to problem 66. Problem 67, calculate the standard molar enthalpy of formation of nitrogen monoxide from the following data. In other words, don't cheat and just look it up in the appendix. Yeah, more of the same. So I would flip the second equation and then add them. That would cancel out the NO2 and one of the oxygens. And then I'd be left with N2 plus O2 gives me 2NO, which is double what I want, because they want the molar enthalpy of formation. Enthalpy of formation, or heat of formation, for a compound is for exactly 1 mole of that compound. So if you don't have 1 mole of that compound in the product side, then you need to multiply or divide accordingly in order to make it a 1. But yeah, I don't see anything interesting here. I have a more interesting Hess's law problem in my physical textbook, so let's grab that one. So it's, which one of these is it? I believe it's 63. So it says we've got 3 reactions this time. This makes things a bit more complicated. So we've got H2 gas plus F2 gas gives us 2HF gas. And we've got carbon solid plus 2F2 gas gives us CF4, and is that a gas? Yes, it is. And then we've got 2C plus 2H2. Carbon is solid and hydrogen is gas, giving us C2H4 as a gas. Okay, and for each of those we've got different delta H values. So we've got delta H equals negative 537 kilojoules for the first one. Delta H equals negative 680 kilojoules for the second one. And delta H equals positive 52.3 kilojoules for the third one. And they want delta H for the following overall reaction. They want delta H for C2H4 plus 6F2, and those are gases, forming 2CF4 gas and 4HF gas. Okay. Let's see. So, like I said with the previous example, first thing I would look at are the things in this overall reaction that only show up in one of these component or step reactions. So, C2H4 only shows up in the third reaction. F2 shows up in multiple places, so we'll ignore it for now. CF4 only shows up in the second reaction. and HF only shows up in the first reaction. Okay, so those guys will help me determine what sort of flipping I need to do, if any. So I need HF on the product side and I need CF4 on the product side. I must not touch these equations in terms of flipping. Maybe I'll need to multiply them later or divide them, but no flipping. So those two equations locked in terms of which side everything is on. The third equation, I need the C2H4 to be on the left. Since this is the only source of C2H4, this must be flipped. So C2H4 gas yielding 2 solid carbon plus 2 hydrogen gas. That's going to be a delta H of negative 52.3 now that I've flipped it. Okay. So that takes care of that, and I just need one of it on the left-hand side, so that part is also good. I need 2 CF4s and I need 4 HFs, which means I need to double reactions 1 and 2. I need to multiply each of those by 2. So multiply all of this by 2 and multiply all of this by 2. And that would also mean, of course, that I'd need to multiply these by 2. So I guess I'll just put a 2 in front of them. But yeah, after that everything should be good to go, and I should be ready to just combine the equations as is. So let's see, I would have 2H2 over here. Let me cross this one out since we flipped it. Don't want to mistakenly read it. So we've got 2H2 on the left side here, and we've got 2H2 on the right side here. Those will cancel each other out. We've got 2 times F2 on the left side here, and we've got 2 times 2F2, so that's 4F2, also on the left side. So if I add those, 2 plus 4, that's 6F2, which is what we should be getting. We've got 2 times 2HF is 4HF, which is what we're supposed to get there. Second equation, we've got 2 carbon on the left there, and we've also got 2 carbon on the right in the blue equation, so those will cancel out, which is good. There shouldn't be any raw carbon in the overall equation. Let's see. What else have I not accounted for? 2 times CF4. That shouldn't cancel out. And then we've already canceled out the carbon. And we've already canceled out the hydrogen. And just 1 C2H4. So yeah, we're good to go. Okay, then delta H for this overall process is going to be 2 times negative 537 plus 2 times negative 680 plus just 1 times, since we flipped it, it's negative 52.3. And if I go ahead and plug those in, we've got 2 times negative 537 plus 2 times negative 680 plus negative 52.3. No decimals, 1 decimal, rounding to 1 decimal, it's negative 2486.3. Negative 2486.3 kilojoules. And there we have it. So there's delta H for that overall process. And yeah, that's how you do a Hess's law problem. Now, I showed you earlier an illustration of how you can use the change in the temperature of a solution surrounding a bunch of atoms in a reaction to determine what the heat of formation is. Let me pull up that diagram again so that you know what I'm talking about. This diagram right here. But we haven't determined yet, we haven't shown yet what the relationship is between the temperature of a solution and the amount of heat that it loses or absorbs. So that's what we're headed to next. Our next subtopic of chemistry, or thermochemistry rather, is calorimetry. Next up, we're talking about calorimetry. Calorimetry. Okay, so what's calorimetry all about? Basically, it's about being able to relate changes in the amount of heat energy to changes in temperature of a given object. So the key equation for calorimetry, the big equation to remember, is that Q, the heat, is equal to mc delta T. Some people pronounce this Q equals MCAT because, you know, the delta kind of looks like a capital A. And if you're a pre-medical student, there's an exam you need to take eventually, which is called the MCAT or MCAT. So there you go. I once had a student who asked me to tutor him for the MCAT. I accepted his request initially because he didn't say that it was for the MCAT. He just said he wanted to review some physics. And once I held that first session with him, he explained to me that he's studying for the MCAT, and I told him he needs to go and try somebody else. And that, you know, I'll help him with the physics and chemistry part as much as I can while he's looking for someone else. And he kind of liked what he was getting from me, even though I knew he could have gotten something better. So he kept on seeing me, and I kept on asking him if he was, you know, looking for another MCAT tutor. And eventually I just kind of gave him an ultimatum and told him, okay, this week is the last week. You have to go find somebody else because there are some advanced topics in here that I can't teach you. And yeah, that was fun. That's gonna go into my, well, actually, I don't know if it's gonna go into that video. I plan on making a video eventually talking about how to get rid of unwanted clients, but that video is probably gonna be most focused on like the rare but extra terrible client that you absolutely have to get rid of. This wasn't the case with him. He wasn't a bad client. It's just that I didn't feel right continuing to accept payment from him when I knew that I wasn't the best person for the job. So I don't know if that should be included or not. But that video won't be coming out for a while. I need to finish this chemistry series first. So Q equals mc delta T. So what are these things? So Q you're already familiar with. This is the change in heat. This is the change in heat. M, that's going to be the mass in grams. Typically in grams, though it could be in kilograms if you really wanted it to be. Then delta T, this is the change in temperature. Temperature change. And this needs to be either in kelvins or Celsius degrees. Note, Celsius degrees, not degrees Celsius. There's a difference between the two. If I say 10 degrees Celsius, then what I'm talking about is the actual temperature being 10 degrees Celsius, which is kind of chilly. On the other hand, if I say 10 Celsius degrees, then that means a change of 10 units on the Celsius scale. So going from 80 degrees Celsius to 90 degrees Celsius would be a delta T of 10 Celsius degrees, not a temperature of 10 degrees Celsius. Probably a minor nitpick that most of you won't care about, but I think it's kind of important to be clear about this. When it's Celsius degrees, we're talking about the difference between two temperatures. When I say degrees Celsius, I'm talking about a temperature. But anyway, that's the temperature change in kelvins or Celsius degrees. It doesn't matter which is which, because in terms of temperature change, like I mentioned in the last video, I think I mentioned it in the last video anyway, a change of, say, 20 degrees Kelvin, if something is 20 kelvins warmer than it used to be, then it's also 20 Celsius warmer than it used to be. Because going from, let's say for example, if I go back to from 80 degrees Celsius to 90 degrees Celsius, well, in kelvins that would be 273 plus 80 is 353 kelvins. To, let's see, 273 plus 90 would be 363 kelvins. So yeah, a 10 degree increase in Celsius is still a 10 degree increase in kelvins. So it doesn't matter. A change in kelvins or a change in Celsius degrees, they're interchangeable. Okay, and finally, we've got C over here. So C is what's called the specific heat capacity. Lowercase c, specific heat capacity. I believe I might have mentioned this very briefly in the very first video in this series when I was talking about intensive versus extensive properties. Specific heat capacity is an intensive property. It depends on the substance that's having its temperature changed. Metals usually have low specific heat capacities. Their temperature changes very easily. Nonmetals tend to have higher specific heat capacities. Their temperatures don't change as easily. It takes more heat to warm up most nonmetals in comparison to metals. But there's also something else I mentioned in that video, which was called just heat capacity. So just plain old heat capacity. Plain old heat capacity. Heat capacity is an extensive property. It depends on how much material you have. So heat capacity, which is represented with a capital C, is equal to just the first two parts of this equation. The mass times the specific heat capacity. So in other words, you could rewrite this equation as Q equals big C times delta T. You could write it as Q equals big C times delta T, where big C is equal to M times little c. So yeah, heat capacity, extensive property, determines how much heat is required in order to increase the temperature by 1 degree Kelvin or 1 degree Celsius, or I should say 1 Celsius degree. And that's actually something I take advantage of when preparing my tea. So say hello to our good friend the Turkish coffee pot again, which I ironically use for tea because I don't drink coffee. Part of the reason I bought this is because, well, I prefer it over a teapot. See, with a teapot, first of all, most teapots are going to be a lot bigger. So it just was too much for my needs. Usually when I make my tea, I just make 1 cup's worth and I'll be on my way. But the other advantage of this thing being small is that the smaller it is, the less mass it has, and the less mass it has, the less heat energy that needs to be wasted warming up the metal before warming up the water inside of it. If there's less metal to heat up, then my water will heat up quicker and I'll be able to drink my tea sooner. I'm kind of an efficiency nerd like that. In fact, not only do I use this smaller container, I also usually only fill it about halfway with water before heating it up, and I don't heat the water to a boil. Usually I heat the water up to around somewhere between 50 to 60 degrees Celsius. So that's great because it's less of a temperature change. So less water going in, so less mass. The specific heat of water, I can't really change that, but by using less water, the total heat capacity is less because it depends on the mass, which I'm using less of. So using less water reduces the mass, and not waiting until it heats up to a boil reduces the amount of temperature gain that I need, which overall helps significantly reduce the total amount of heat that needs to go into my tea, which also then reduces the amount of time it takes for me to prepare my tea. And sometimes if I want to just put, my tea on the stove and watch like a 15-minute video and not have to worry about my tea boiling over, then sometimes I'll do the opposite. Sometimes I'll fill this all the way with water, or 2/3 of the way or something like that, so that it takes longer to heat it up, so that I can watch my videos in peace. Look at me, professional multitasker. Not really. I don't encourage multitasking overall. I think it's a very, very inefficient way to do things because you feel like you're being more productive, but you really are being less productive. There have been plenty of studies proving it. I don't encourage multitasking, unless you want to do it with your entertainment. But with your work, definitely do not multitask. Anyway, so that's just a good real-life example of how I use chemistry to run my life more efficiently. Though you probably didn't need to know chemistry to realize that more water will take longer to heat up. Unfortunately, I can't do that with rice. The problem with rice is that it needs to sit in the hot water for long enough to actually get softer. So using less water, not going to help. I actually need it to spend time at high temperatures and not just get it to a high temperature quickly. But now I'm talking too much about what I do in my kitchen, and you're not here for a lesson on cooking. You're here for chemistry. So I think I've said everything that needs to be said here. I think we should just go ahead and do an example. Let me see. Oh, actually first let me show you these tables of specific heats. So, like I said, specific heat is an intensive property. It depends on the identity of the substance. For different substances, they have different specific heats. If you notice the units for specific heat right there in the third column label, it says specific heat, and then in parentheses, joules per gram degree Celsius. That should say joules per gram Celsius degree, so there I go calling out the typos of the authors of the book. But You know, it's not much to complain about. There's also a more expanded table that we might use later, but let's go ahead and look at some of the problems that I have regarding calorimetry. Okay, so these should be some quick warm-up problems. Number 4 says, calculate the heat capacity in joules and in calories per degree of the following: 28.4 grams of water, 1 ounce of lead. I don't feel like converting ounces to grams, so let's just do part A. And also let's define calories. So 28.4 grams of water. What is the heat capacity for 28.4 grams of water? So, first off, the specific heat capacity of water, I'll call it C sub H2O, is equal to 4.184 joules per gram Kelvin, or joules per gram Celsius degree. Doesn't matter which one you use, because like I said before, in terms of temperature changes, Celsius degrees and kelvins are equal. They're interchangeable, they're the same thing. Now, if you've done physics, then you might remember this number as 4.186. So what's going on? Well, apparently the specific heat capacity used by physicists and chemists are based on different temperatures. You see, the specific heat capacity actually changes while the temperature of water changes. For a lot of substances, their specific heat capacities are not constant, but you can treat them as if they're almost constant because they usually don't change too much. So the specific heat of water at, say, 25 degrees Celsius is different from the specific heat of water at, like, 20 degrees Celsius. And I believe that physicists use a different definition of room temperature. So I think they use 4.186 because it's the specific heat capacity of water at 20 degrees Celsius, as opposed to chemists who use 25. At least I think that was the reason for the difference, but I might be wrong. You can Google it. But yeah, in chemistry it's 4.184, in physics it's 4.186, because reasons. Anyway, specific heat of water is 4.184 joules per gram degree Celsius. Also, 1 calorie is defined as exactly 4.184 joules. So this is an exact conversion right here, so infinite sig figs. So yeah, a calorie is defined as exactly 4.184 joules. A calorie is defined as the amount of heat it takes to warm up 1 gram of water from, I think the official definition was from 24 degrees Celsius, from 24.5 degrees Celsius to 25.5 degrees Celsius. I think that was the formal definition, but again, you can look that up while also looking up the reason why physicists use a different value. So don't take my word for it, go Google it. But yeah, that's a calorie. Then there's something we'll need to know about for later, which is the kilocalorie. 1 kilocalorie, of course, is 1,000 regular calories. That's not mind-blowing at all, or anything you couldn't just conclude on your own. But one thing that may not be so obvious, it wasn't obvious to me anyway, is that a nutritional calorie is actually equal to a kilocalorie and not, a physical calorie. So yeah, 1 kilocalorie, sometimes called 1 kcal by the cool kids. It's not just the cool kids. The professors call it kcal too. Anyway, 1 kcal is equal to 1 calorie with a big C. So calories with a capital C are nutritional calories, which are equal to 1,000 physical calories. Because I remember being on a treadmill one time, and I knew my physics, and I knew the amount of energy I was expending was far more than 4.184 joules, given the rate that I was running at. And yet the meter, the thing on the treadmill that reads how many calories you've burned, it was taking forever to add 1 calorie to my total calories burned. And that's when I had to look it up, and that's when I realized, oh, okay, the nutritional calorie is 1,000 physical calories. So yeah, probably one of the dumbest things in... I don't even know what word I would use to complete that sentence. It's just one of the dumbest things I've ever seen. We call them both calories, but one is with a capital C, so it's worth 1,000 times more. That was never obvious to me. And the things we do to appease normal, non-scientific people. Am I right? Anyway, back to the problem at hand. So we need to figure out the heat capacity of 28.4 grams of water. Okay, well, we know the specific heat capacity, so the heat capacity is going to be 28.4 times 4.184. Easy peasy, lemon squeezy. And that comes out to 118.8256, rounding to 3 sig figs. That's 119 what? Well, specific heat capacity is joules per gram Celsius degree. So heat capacity, if I multiply by grams, then that would cancel the grams in the denominator of joules per gram Celsius. So that's joules per Celsius degree, or if you prefer, joules per Kelvin. I think in most textbooks it'll be written as kelvins, but again, a Celsius degree change and a Kelvin degree change are the same, so it shouldn't bother you either way. Okay, so there's the heat capacity of 28.4 grams of water. Let me see, is there anything else interesting in this problems list? We've got... oh, they also wanted it in calories per degree. Well, in calories per degree, you just divide by 4.184 to go from joules to calories, so yeah, I'll ignore that part. Anyway, number 5, more of the same. Number 6, how much heat in joules and calories must be added to a 75 gram iron block with a specific heat of 0.449 joules per gram Celsius to increase its temperature from 25 Celsius to its melting temperature of 1535. Okay, here's an interesting problem. Well, I mean, it's more interesting than the previous one, but compared to problems we'll be seeing later, probably not that interesting. I need to stop using the word interesting so easily. It devalues the word and weakens its meaning. Let's see, so it's a 75 gram block. It's got a specific heat capacity of 0.449. Notice, much less than the specific heat capacity of water, almost 10 times less. And that's joules per gram Celsius degree. And then from 25 to 1535. So the initial temperature is 25 degrees Celsius, and did they? No, they did not. They did not add a 0.0. And the final temperature is 1535. 1535 degrees Celsius. Okay, then the temperature change is the final temperature minus the initial temperature. Since we go up to a higher temperature, we should have a positive temperature change. So 1535 minus 25 should be 1510, and that's Celsius degrees, since it's a temperature change. Okay, if we then calculate how much heat in joules, and they also want it in calories, how much heat in joules and in calories is required to achieve this, go back to our good old Q equals MCAT. Q equals 75.0 times 0.449 times 1510. And that should give us the energy in joules, because so we've got grams here, we've got joules per gram Celsius here, and we've got Celsius here. So grams will cancel with the grams in there, and Celsius will cancel with the Celsius in there, and that leaves the joules in the specific heat capacity. So what will this be equal to? I guess I'll write it up there. 75.0 times 0.449 is 33.675, round to 33.7, and then 33.7 times 1510 is 50887, round to 50,900 for 3 sig figs, so that's 50,900 joules. That's a lot of joules. It would be more appropriate to represent this as kilojoules, so it's 50.9 kilojoules. And if I want to convert it to calories, 1 calorie is 4.184 joules, so maybe I'll do it up here. We've got 50,900 joules. Every 4.184 joules is equal to 1 calorie. So 50,900 divided by 4.184 is 12,165, so that's 12,200 calories. 12,200 calories, or 12.2 kilocalories, or 12.2 nutritional calories if you prefer. Okay, so there's that one, and I should probably draw an arrow to there just so anybody viewing it later who skipped parts of the video isn't too confused. Though really that's on you if you skipped parts of the video. You can just use the left and right buttons on your keyboard to rewind, unless you're watching this on your phone, in which case you don't have such convenient shortcuts. At least not as far as I'm aware, because I don't really have a habit of watching YouTube on my computer, or wherever you might be watching this. I should keep these videos in case something bad happens with YouTube. Anyway, let's take a look at some of the other problems, see if there's anything worth doing there. How much heat in joules and calories is required to heat a 28.4 gram ice cube from negative 23 Celsius to negative 1? I imagine we would need the specific heat of ice, which is probably available in one of those tables, but otherwise pretty much the same as number 6. Number 8, how much would the temperature of 275 grams of water increase if 36.5 kilojoules of heat were added? Okay, so for this one they gave you Q ahead of time, and they gave you the mass. You should know the specific heat of water is 4.184, so what they're asking for is the delta T. But you should be able to do that on your own. Just remember, the specific heat of water is in joules per gram Celsius, so to get the right units, you should convert the 36.5 kilojoules to 36,500 joules. But otherwise, I think you can handle that just fine. Number 9, 14.5 kilojoules of heat were added to 485 grams of liquid water. How much would its temperature increase? Okay, so pretty much the same thing. Warning about number 7. I kind of mentioned it, but to make it extra clear, the specific heat of ice is not the same as the specific heat of water. When the state of matter changes, so does the specific heat. And I don't know if I mentioned it before, but specific heat is the same as specific heat capacity. So, whenever you hear me say specific heat, it's the same thing as specific heat capacity, but whenever you hear me say heat capacity, it means the big C, not the little c. Let's look at another set of problems. Let me see. Anything in here that might be worth doing? A piece of unknown substance weighs 44.7 grams and requires 2110 joules to increase its temperature from 23.2 to 89.6. What is the specific heat of the substance? And if it's one of the substances found in table 5.1, what is its likely identity? Okay, and number 11 is kind of the same thing. Let's do this one. It's pretty easy, but still worth doing to help hammer in the fact that specific heat capacity is an intensive property. Intensive properties depend on what the substance is, and therefore can be used to identify the substance. So let's go ahead and do that one. So we've got a piece of unknown substance. It's 44.7 grams. I'm just going to go ahead and write it into the equation. So Q equals MC delta T, 2,110 joules, equals 44.7 grams times 4.184. Wait. No, it's not water. Restart. And it looks like, is the yellow dead? Yeah, it's pretty much dead. Okay, to the trash it goes. Hooray! It's my least favorite of all the colors in here, because I know from watching the videos that you guys can see it clearly, but from my angle it's kind of difficult for me to see. I actually have to squint and lean over to read it. But yeah, goodbye to the yellow marker. What should we put in its place? Well, if I pick the color I want, I'm going to have some clashing colors later, so let's just go with this one. I believe that's magenta. Shouldn't clash too much with peach, or shouldn't, maybe clash isn't the right word, but shouldn't blend too much with peach. Anyway, 2110 joules equals 44.7 grams times an unknown specific heat capacity times a temperature change of 89.6 minus 23.2. Okay, 89.6 minus 23.2 should be 66.4. Let me write that up there, 66.4. So, yeah, 2110 divided by 44.7 is 47.2 when rounded to 3 sig figs. 47.2 divided by 66.4 is 0.711 when rounded to 3 sig figs. So specific heat capacity 0.711. The spacing there is kind of weird. Let me try that again. Specific heat is 0.711 joules per, let's change it up and say gram Kelvin. Shouldn't matter if it's Celsius or Kelvin, so get used to it. I'll try to change it up every now and then to help hammer that point home. Hammer that point home? Is that an expression people use? Drive the point home. Then what's hammer it in, drive it home? I think those are the correct expressions. But I'm no English tutor. Let me see. So they said they wanted us to look at the table and identify the substance. Let me see. It's probably in this second table somewhere. So, 0.711. Looks like, if I look at the very bottom of the table, the substance may very well have been silicon. Or silicone, or silicon. I'm not going to dictate to you what the correct pronunciation is. I call it silicon, but when you get to college, if you're not in college already, you will hear all three of those different pronunciations, and as to who pronounces it right, well, that's a political question. And I'm not ready to talk politics at this time. Oh, there will be political topics on this channel later, specifically when it comes to education policy, but all in due time. First things first, I gotta help the chemistry students. Let me see. So that was that problem. Was there anything else interesting over here? 11 is just more of the same. Okay then, let me see what I've got over there. Oh, this is a nice conceptual problem. So we've got a 500 milliliter bottle of water at room temperature and a 2 liter bottle of water at the same temperature. They are both placed in a refrigerator. After 30 minutes, the 500 milliliter bottle of water had cooled to the temperature of the refrigerator. An hour later, the 2 liters of water had cooled to the same temperature. When asked which sample of water lost the most heat, one student replied that both bottles lost the same amount of heat because they started at the same temperature and finished at the same temperature. A second student thought that the 2 liter bottle of water lost more heat because there was more water. A third student believed that the 500 milliliter bottle of water lost more heat because it cooled more quickly. A fourth student thought that it was not possible to tell because we do not know the initial temperature and the final temperature of the water. Indicate which of the answers is correct and describe the error in each of the other answers. So you might want to pause the video and give this one some thought. I'll give you a little bit of a hint. Look at the Q equals mc delta T equation, and also another thing that I haven't really stated out loud yet, which is what determines whether or not heat flows from one place to another, and how quickly the heat does flow from one place to another. So those are things to think about. But yeah, pause the video and give it some thought. I'm just going to carry on, assuming that you have paused and have thought about it. I'm sure a good chunk of you haven't, but we don't want this video to be too long. We saw how long the last video turned out, and I'd rather not repeat that if I don't have to. Though if I do have to, I will. I want to kind of keep going at this pace of 1 chapter per video. So first student said that both bottles lost the same amount of heat because they started at the same temperature and finished at the same temperature. This is not true, because if we write down Q equals mc delta T, if they start at the same temperature and finish at the same temperature, which is true, then they have the same delta T. Since they're both water, they have the same C, but they don't have the same M. The 2-liter bottle, it's got a higher volume of water and therefore a higher mass of water. And since it's got more mass, it's going to lose more heat for the same amount of temperature change. So student number 1 is wrong. The second student thought the 2-liter bottle of water lost more heat because there was more water. That is exactly correct. A third student believed that the 500 milliliter bottle of water lost more heat because it cooled more quickly. No. Cooling more quickly doesn't mean anything. In fact, if it cooled more slowly, it would be better off, because the sooner you cool down to the refrigerator's temperature, the sooner you stop cooling down. Once you're at the same temperature as the refrigerator, the change in temperature just stops. Temperature determines whether or not heat flows between two things. If there is no temperature difference between two things, if you bring down the temperature of your, half-liter bottle to refrigerator temperature early, then it's lost all the heat it's gonna lose. Now that it's at the same temperature as the refrigerator, it can't lose any more heat. Of course, in the real world, it will continue to lose heat because it'll gain heat from the surroundings outside the refrigerator. And no matter how good the refrigerator insulation is, heat from the outside is coming in, so the refrigerator has to start up again and recool everything after it warms up a couple degrees. Anyway, student number 3 believed that the 500 milliliter bottle of water lost more heat because it cooled more quickly, so we've debunked that one. Cooling more quickly has nothing to do with it. The reason it cooled more quickly was because there was less water to cool in that bottle. Assuming that the heat was being sucked out at a constant number of joules per second, then of course the one with the higher heat capacity, the one with more mass, would take longer to lower its temperature. Student number 4 thought that it was not possible to tell because we don't know the initial temperature and final temperature of the water. That's wrong, because we don't need to know the initial and final temperature. We just need to know the fact that they were the same for both bottles. We just need to know that they were the same for both bottles, and that's enough for us to know that the delta T isn't making the difference, the C isn't making the difference, the M is all that's left to make the difference. Q equals MC delta T. And by the way, I just remembered this right now, work on your intuition and work on associating the idea of higher heat capacities and higher specific heat capacities being associated with lower rate of temperature change. The higher the specific heat capacity, the harder it is to change the temperature. Also, the more mass, the harder it is to change the temperature. The more stuff you have to heat, and the more heat per gram it needs in order to go up by 1 degree, the slower it will heat up. So work on developing that intuition if it's not obvious to you already. Okay, so that was the third set of calorimetry problems. I think now is about time to talk about the first law of thermodynamics. The first law of thermodynamics. We'll talk about the second and third laws when we actually get to the proper thermodynamics chapter. But the first law of thermodynamics, you probably already know it. The first law of thermodynamics, capital L, capital T. Actually, I don't know if they absolutely need to be capitalized, but it feels like a title where capitalization would be appropriate, so It's whatever. First law of thermodynamics. What does it say? Basically, it's the law of conservation of energy. Energy cannot be created or destroyed. Energy cannot be created or destroyed. But can be transferred from one object to another. Can't be created or destroyed. The total energy of the whole universe is constant. The only thing that can change about it is the form of the energy and the objects carrying that energy. So in mathematical terms, what this means is Q for the universe is always equal to 0. And since a universe is always composed of a system plus its surroundings, if you have a system, then the surroundings are the rest of the universe. So whatever change in heat happens to a system, the change in heat that happens to the rest of the universe, the surroundings, will be the opposite. Q system plus Q surroundings equals Q universe equals 0. In other words, any heat gained by the system must be lost by the surroundings and vice versa. And of course, the universe is kind of too big for us to think about, but if you were to do some sort of exchange of heat within a well-insulated container, a container so well-insulated that it could be treated as an isolated system, then you could break that isolated system up into a part that you're interested in and a part that you're not interested in, and call one of them the system and the other one the surroundings, and then apply this law. So for example, if I were to put an ice cube into a thermos full of warm water and then close the thermos really quickly so I don't allow too much air to get in, then you could say, depending on what you're interested in, you could say that the ice cube is the system and the rest of the water inside of your quote-unquote isolated thermos is the surroundings, or vice versa. It really doesn't matter. What matters is the total change of heat inside that thermos is approximately 0. No thermos is perfect, but we can probably get away with it as long as we don't let too much time pass. So yeah, that's the first law of thermodynamics. If heat is gained from one place, then it's lost from another place, and vice versa. That didn't even sound like it came out right. Anyway, you get the idea. The heat must have come from somewhere. If you lose heat, then you lose it to someone, and someone must have gained that heat, or something. So, with that out of the way, I think it's time to look at maybe some thermal equilibrium problems, which are basically problems involving this first law of thermodynamics. You put a hot thing with a cold thing, and you leave them alone for a while. Eventually they exchange enough heat that their temperatures become the same, and you do some calculations. So that's what we're headed towards. Let's take a look at what we've got. Number 18 says how many milliliters of water at 23 Celsius with a density of 1 gram per milliliter must be mixed with 180 milliliters of coffee, which I don't drink, at 95 degrees Celsius, so that the resulting combination will have a temperature of 60 degrees Celsius. Assume that coffee and water have the same density and the same specific heat. Okay, so they didn't want to give us the specific heat of coffee, which is fine, because that's kind of difficult to do. How do you determine the specific heat of coffee when people mix their coffees with all sorts of concentrations? Okay, so This one is kind of easy because they want the specific heats of both to be the same. But yeah, let's go ahead and do it. So I'll start this on another sheet. Or do I have room to do it on this sheet? Nah, I'm not going to chance it. Okay, so we've got... let's see, we've got for the water, we have... Oh, they want to know how many milliliters, so we don't know the volume of water yet. So that means we also don't know the mass of water yet. That's currently unknown. And then the volume of water. We know that the starting temperature of water, so T water initial, is going to be 23 degrees Celsius, nearly room temperature. Let's see, it must be mixed with, we've got 180 milliliters of coffee. 180 milliliters. And the coffee is at 95 degrees. So T coffee initial is 95 degrees Celsius. The resulting combination will have a temperature of 60 degrees Celsius. So T final is 60 degrees Celsius, and that should be the same for both of them. If it weren't the same for both of them, then they would still have a temperature difference and they would not be done exchanging heat. So once they are done, they should have the same final temperature. And since in this case they gave us the final temperature, it's not a problem. But later on we'll see problems where you need to come up with the final temperature. And a good way to check that you did it right is to make sure that your final temperature actually is between the temperature of the cold object and the temperature of the warm object. So yeah, if you had to calculate T final for this problem and you got something like 20 degrees Celsius, which is lower than the starting temperature of the water, you'd probably suspect something was wrong. Or at least I would hope you would suspect something is wrong, because that would tell me that you're actually paying attention when doing your problems. But yeah, lost my train of thought. Let me just carry on. Is there any more data here? They say assume the coffee and water have the same density and the same specific heat. So the density was 1 gram per milliliter, which basically tells me that 1 milliliter equals 1 gram. So 180 milliliters is 180 grams. The mass of the coffee is 180 grams. And C for water equals C for coffee equals 4.184 joules per gram Kelvin. Okay, let's see. Wow, it looks like it's really floating up there from your perspective, but it's only like half an inch high from my angle. But yeah, that fan is really doing its work. And yeah, there's no more data to pick up from there. Okay, so we're further going to assume that the water and coffee exchange heat with each other within an isolated container. So basically, if I were to draw an isolated system like this, and of course the coffee and water would be thoroughly mixed with each other, so what I'm about to draw is not going to be very realistic, but let's pretend you have a solid block of water here and a solid block of coffee here, and they're contained within some sort of really good insulating container so that they're isolated from the rest of the world. And so no heat goes in, no heat goes out, but heat can be traded between the water and the coffee. And of course the coffee is hot, so it's going to give heat, it's going to lose heat to the water. Already used that color, let's do this one. So basically this is the direction of heat flow. So you could say Q system equals negative Q surroundings, and you can decide for yourself whether you want the water or the coffee to be the system, or you can also say Q lost equals negative Q gained, or you can also say Q water equals negative Q coffee. Whatever makes the most sense to you, as long as you understand that the amount of heat lost by the coffee equals the heat lost by the water. So yeah, regardless of which of these two you're looking at, what I'm going to write next should be the same. There, that'll keep the fan from blowing it over. What I really should do is just move the fan out of the way. Maybe I'll do that later. So what do we have? We've got an unknown mass of water. So MH2O times 4.184 times delta T for water is 60 minus 23, which is going to be 37. 37 is equal to negative Q lost by the coffee what did I probably should have written this as Q gained equals negative Q lost, but it has the same meaning in terms of math. Anyway, I'm getting too distracted. Mass of coffee is 180 grams. Specific heat of coffee is treated as being the same as water, so 4.184. And temperature change of coffee from 95 to 60 is negative 35. See, that's why that negative sign is needed, so now the negatives can cancel out. And that way we can actually calculate a positive mass. If you got a negative mass, you did something wrong, which probably means you forgot the negative either here when writing, this equation, or maybe you even forgot the negative when calculating the delta T for coffee. But yeah, 4.184, I can cancel that on both sides and divide both sides by 37 and we're done. So let's see. 180 times 35 is 6,300. Divide by 37, that's 170.27, which of course I will just round to 170 because I need 2 sig figs. So yeah, the mass of the water is 170 grams with 2 sig figs. Probably better to write it as 1.7 times 10 to the 2 grams. That way it's extra clear that it's 2 sig figs. But they didn't want the mass of water, they wanted the volume of water. And they said the density was 1 gram per milliliter, so really you divide by 1, or you multiply by 1 milliliter over 1 gram times 1 milliliter for every 1 gram. And there you go. Grams become milliliters. So it's 1.7 times 10 to the 2 milliliters of water, or 170 milliliters, depending on how you want to write it. Okay, so that was problem 18. So we had the convenience of the specific heats being equal on both sides and canceling out. Is number 19 any different? We've got a 180 gram cup of coffee at 95, and there's a silver spoon, and we've got its specific heat there. It's placed in the coffee, and the two are allowed to reach the same temperature. Okay, seems interesting. What about number 20? 45 gram aluminum spoon at 24 Celsius is placed in 180 milliliters of coffee at 85 Celsius, and the temperature of the two become equal. What's the final temperature? And the first time a student solved this problem, she got an answer of 88 Celsius. Explain why this is clearly in... Ooh! Could this be exactly what I was talking about? Okay, let's do number 20. Let's do number 20. Okay, so we've got a 45 gram aluminum spoon. Mass of aluminum is 45 grams. We have the specific heat is 0.88. So C aluminum is 0.88 joules per gram Celsius degree. We don't know the temperature change, but we do know the initial temperature of the aluminum. T aluminum initial. There. So initial temperature of the aluminum is 24 degrees Celsius. And it's placed in 180 grams of coffee, so mass of coffee 180 grams. And the specific heat of the coffee, they said to treat it as the same as water, or to treat it the same as water. I don't know why I threw in that extra as. So that's 4.184. Joules per gram Celsius degree. And the initial temperature of the coffee was 85 degrees Celsius. And of course they're left together for a while until their temperatures become equal. And what is the final temperature? Let's answer part B first. So part B was asking, the first time a student solved this problem, she got an answer of 88 degrees Celsius. Explain why this is clearly an incorrect answer. So this is what I was talking about before. If the coffee has the higher temperature and the aluminum has the lower temperature, then coffee is going to lose heat to the aluminum, so the coffee temperature is going to go down, the aluminum temperature is going to go up, and they're going to meet somewhere in between 24 and 85. 88 degrees Celsius is not between 24 and 85. So that's how you know immediately that something went wrong with that first calculation. You should not be getting something like 88 degrees. Okay, now with that out of the way, let's calculate T final. Oh my, I really should just move the fan. Give me a second here. Maybe if I change the angle. Does that work? Yeah, that should work. And, oh, I can put that away. Okay, I think now we won't have any fan problems. Let me check. Yeah, doesn't seem to be floating. Okay, where were we? So, calculating T final. So, we know that let's see, it's the aluminum losing heat, or no, the aluminum is gaining heat, so let's say Q aluminum equals negative Q coffee. Of course, if you put the negative on the other side of the equation, doesn't matter. It'll all simplify and give you the same result anyway. So let me see here, Q aluminum and Q coffee. So for aluminum, it's going to be 45 grams times 0.88 joules per gram Celsius times a temperature change of T final, which we don't know, minus 24. And then for the coffee, so that's going to be equal to the negative of, for the coffee, it's 180 grams times 4.184 joules per gram Celsius times a temperature change of T final minus 85. Okay, so one thing you might do is multiply 45 and 0.88 together, and multiply 180 and 4.184 together, and then distribute this over T final minus 24, and distribute that over T final minus 85, and that would be a mistake. Well, it wouldn't be a mistake per se, but it's not what I would recommend because you're just making things more difficult for yourself. You only have to distribute on one side. You only have to distribute on one side. So what you can do is divide both sides by 45 and divide both sides by 0.88. And that way on the left-hand side you just get T final minus 24. So let me do that. So you've got T final minus 24 is equal to negative, and we've got 180 and 4.184 over 45 and 0.88 times T final minus 85. You only need to distribute on one side, which is great. Less distribution is less work. So 180 times 4.184. I'm guessing that's going to round to 2 sig figs because I can already see where this is going. So 753.12, I'll round that to 750. 750 over 45 is 16.6. I'll round that to 17. 17 over 0.88 is 19.3. I'll round that to 19. So we're left with T final minus 24 is equal to negative 19 times T final minus 85. Okay, distribute the negative 19. We've got T final minus 24 is equal to negative 19 T final plus, what's 19 times 85? 1615, which of course in 2 sig figs would be 1600, where the zeros don't count. 1.6 times 10 to the 3 if you prefer writing it in scientific notation. Add 20 T final to the left-hand side. So that would be, add 19 T final to the left-hand side, making it 20 T final. Minus 24 equals 1600. Now, if I add 24 to both sides, then I get 20 T final equals 1600. And the reason for this is because 1600 plus 24 is essentially the same as 16 with no decimal places plus 0.24. So no decimals plus 2 decimals gives you 16.24, which you round to no decimals, so 16. Similar logic applies to this right here. I should actually have these both written in scientific notation in order to see that. So maybe I should write it as 1.6 times 10 to the 3 plus, that's going to be 0.024 times 10 to the 3. 1 decimal place, 3 decimal places. So yeah, 1.6 times 10 to the 3 or 1600. No matter which of these three ways you're looking at it, it's still 1600. Which, I know, it feels kind of stupid, and that's why I don't really like the sig fig rules all that much. The dirty truth about sig figs is that they don't always work. I think I said that in the second part of this chemistry series. We'll see a good example of where the sig figs will fail you when we get to second semester content and talk about equilibrium. There will be a case or two I might be able to show where the sig fig rules will definitely fail you. Oh, great. I can see well, it's not as bad. The fan is still trying to lift up the paper, but doesn't look like it'll succeed. Anyway, 20 T final is 1600, divide by 20, and that should give us, let's see, so by 10, 160 over 2, so that's 80. So T final equals about 80 degrees Celsius, give or take. Now let me see, if I did keep it as 1624 and divided by 20, that would be 81.2. So yeah, so it would have made a 1 degree difference when rounding to 2 sig figs. Okay, and I probably should put a decimal point down here to emphasize that this is 2 sig figs. That 0 does count. All right. I think that takes care of that problem. Do we need to see anything else from that page? 21. Oh, God, it's in Fahrenheit. So if you see Fahrenheit, you have to convert to Celsius, because we don't have specific heats in joules per gram Fahrenheit degree. Or if we do have them, they're not in my book. So, yeah, that's 21. 22, 70 gram piece of metal placed in 100 grams of water. Okay, so yeah, we've already done something like that, so I think we're ready to move on to something else. So now that we know about calorimetry, we can take a look at how calorimetry can be used to determine the heat of a reaction. We already saw that diagram twice now, where whether it's for an exothermic or endothermic reaction, you can measure the change in the temperature of the surrounding solvent for dissolved reactants and products, and use that to measure how much heat was gained or lost by those atoms. So that's what we're getting to right here. Let's pick a good representative problem so that we don't have to do all of these. What does 23 say? Reaction produces that many kilojoules of heat, which is trapped in 30 grams of water initially at 26.5 degrees Celsius in a calorimeter. What is the resulting temperature of the water? Okay, so for that they just kind of want us to work backwards. So just use Q equals MC delta T and calculate the temperature change. That's pretty much a normal calorimetry problem. We've already seen that. 24, 0.5 gram sample of potassium chloride. is added to 50 grams of water in a calorimeter. If the temperature decreases by 1.05 degrees Celsius, what's the approximate amount of heat involved in the dissolution of the KCl, assuming the specific heat of the resulting solution is 4.18 joules per gram Celsius? Is the reaction exothermic or endothermic? Okay, now we're in business. Now we are in business. So, oh, I didn't switch yet. Let's switch back to our camera. Let me see. So we've got 0.5 grams of KCl, 0.500 grams of KCl, solid, and we dissolve it in 50 grams of water. 50 grams of water. Liquid water. Okay. And they said the temperature increases by 1.05. So the delta T is positive 1.05 Celsius degrees. We don't know what the initial and final temperatures are, and they shouldn't matter to us. We just need the temperature change. Let me see. Anything else? Well, the specific heat of the solution is 4.18 joules per gram Celsius. Whoops, forgot the dash. And that is everything. So they want the approximate amount of heat involved in the dissolution of KCl. I'm going to call it the heat of solvation or heat of dissolution, delta H solvation or dissolution, whichever you prefer. And I'm going to calculate it in kilojoules per mole of KCl. I'm going to calculate it in kilojoules per mole of KCl. So, yeah, that's our target. We don't know what it is yet. Let's see. So, if the temperature rose by 1.05 Celsius degrees, then how much heat was absorbed? It would be the mass of the solution. Remember, the solution is the solute plus the solvent. So that would be 50.0 grams of solvent plus 0.5 grams of solute. 3 decimals, 1 decimal, it will round to 1 decimal. The mass of the solution is 50.5 grams. Don't just use the mass of the solvent, because then, well, you'd be wrong. Mass of the solution is 50.5 grams. So now that I know that, Q for the solution is 50.5 for the mass times the specific heat of the solution is 4.18 times the temperature change, which is 1.05. So if I do that, then I get 50.5 times 4.18 is 211.09. Rounding to 3 sig figs, that's 211, and then 211 times 1.05 is 221.55, which rounds to 222. So it's equal to 222 joules, positive. So that means the solution warmed up, which means the atoms, the potassium and chloride atoms, when they converted into potassium and chloride ions, they lost heat. They lost heat, and it resulted in warming up the solution overall. So for KCl, Q of KCl equals negative 222 joules, or negative 0.222 kilojoules if you prefer. Now then, if I want to calculate the enthalpy of dissolution, then what I need to do is take the amount of heat produced or consumed, in this case produced, divided by the moles of KCl. So let me get the molar mass of KCl real quick. Let's grab our periodic table. I see 39.098 for potassium plus 35.453 for chlorine, and that's 74.551. Molar mass of KCl is 74.551 grams per mole. Okay, so then if I've got 0.500 grams of KCl, 0.500 grams of KCl, then divided by 74.551 grams for every 1 mole, that should give me 0.500 over 74.551, 3 sig figs, 5 sig figs, round to 3 sig figs, that's 0.00671. 0.00671 moles of KCl. So then that many moles of KCl gives me negative 222 joules. 1 mole of KCl ionizing should give me way more joules, because that's way less than a mole. So let's see. I'm going to convert this to kilojoules and plug it in as negative 0.222 kilojoules. So negative 0.222 divided by 0.00671 is going to be, let's see, rounding to 3 sig figs, negative 33.1. So delta H of solvation, or delta H of solution, is equal to negative 33.1 kilojoules per mole of KCl dissolved. So this just shows us one example of how we can get a heat of reaction for, or I guess just an enthalpy of reaction in general for a process, just by measuring how much heat was gained by the water, or in this case the solution as a whole, because having the KCl in there slightly alters the specific heat, usually to a very small degree, but sometimes it really depends on how much solute there's in there. But yeah, so this was the, I wouldn't call it a reaction, but a process. KCl solid goes in water and becomes potassium ion plus chloride ion, and the delta H for this process is negative 33.1 kilojoules per mole. The water got warmer. So this process is, of course, exothermic. Delta H for the atoms was negative, so the atoms released energy. They gave energy to, well, they kind of gave energy to themselves and the water, but mostly to the water, because the water is most of the solution. So they released some of the energy in the chemical bond between the potassium and chloride ion. Some of that energy went to heating the water, but some of it also went to raising the temperature of the potassium and chloride ions themselves. Some people might actually, let's address this. Some people might be asking, or might be wondering, since I calculated Q here for the whole entire solution, including the KCl, isn't that like treating... let me try and figure out how I want to word this. I know what the question is that some students are going to have, but how do I put it into words? So over here, I calculated the enthalpy change for the whole solution, and I said that was the negative of the enthalpy change for the KCl. So some students might ask the question of, am I treating KCl as being the system, but also treating it as being part of the surroundings? And the answer is no. This Q right here doesn't really... It's not about treating the KCl as being part of the system and part of the surroundings at the same time, but rather the heat that's generated by the dissolution of KCl, it's going to increase the temperature of everything in the solution. So this shouldn't be thought of as the heat of just the surroundings. This should be thought of as the total heat that was released by the KCl. I don't know if that's making any sense. I need to pause a bit and think about how I want to word this, because I've got the idea in my head, and I know some students are really paying attention and are justifiably conflicted on this, but how do I word it correctly? Let me think. When you're so good at your chemistry that you understand it in a very abstract sense and have a hard time putting it into words. Oh goodness. That's pretty much the challenge for everybody who wants to be a teacher or tutor or instructor in some capacity or another. Because intuitively, I know why this is okay. But how do I put it into words? Okay, think of it like this. So the QKCl here, this is basically the total energy that got released from breaking the ionic bond within solid KCl. So the negative 222 joules, that was from breaking the ionic bonds. So think of the bonds between the atoms as being the system rather than the atoms themselves. Maybe that's what I should have said from the very beginning. That probably would make more sense. So there's heat that you got from breaking the bonds between the potassium and chloride ions while they were in the solid form, and that heat then got absorbed by, of course, the water, but also the newly made potassium and chloride ions, which, for the potassium and chloride ions, that heat is not going to be stored in bonds because, well, they're just ions floating around in water. They're not bonded to anything. They don't have bonds in which to store any sort of energy. So yeah, I think that's a good justification. I'll think it over some more, and if I can find a better way to word it, I'll probably explain it in a pinned comment. But yeah, this Q solution is basically a measure of the amount of heat that went into the solution, and it must have been a result of heat lost by the KCl. I feel like I'm just talking around in circles and making redundant statements, but anyway, I'll think it over some more, and if I need to clarify it, or if I can think of a better way to word it, then you'll see that in a pinned comment. Let's see. Where do I want to go from here then? Are there any other problems here that might be worth going over? We just did 24, 25. It's another heat of dissolution problem. Oh, we've got concentrations here for 26. What's number 26 say? 50 grams of 0.2 molar sodium chloride added to 100 grams of 0.1 molar silver nitrate. Ooh, and we get a precipitation reaction. Silver nitrate is soluble, sodium chloride is soluble, but when silver ion contacts the chloride ion, they will become solid silver chloride. Let's see, temperature increases as silver chloride forms, assuming the specific heat of the solution and products is 4.20 joules per gram Celsius. Calculate the approximate amount of heat in joules produced. So they just want the amount of heat that resulted from the reaction, but they don't want the heat of reaction. We could still calculate the heat of reaction from this, because all we'd have to do is divide it by, I guess, the moles of anything in this. Well, no, by the moles of the limiting reactant specifically, I would say. Let's go ahead and do this one. I'm interested. Should I do it on a new sheet? Well, I'll start it here, and it'll probably need a new sheet. Let's see, so 50 grams of 0.2 molar sodium chloride at 24.1 degrees Celsius is added to 100 grams of 0.1. Wait a minute. 50 grams? Don't they mean milliliters? Oh. Well, this is a badly written problem. I think they meant to say milliliters and not grams. Yeah, they must have meant milliliters, because if you don't know the density of that solution... Yeah, they must have meant milliliters. That's a typo. Typos happen in textbooks, by the way, so if you see something in your textbook that doesn't seem right, you don't always have to second guess yourself. Sometimes the textbook is wrong. Okay, it's 50 milliliters, so we've got 50 milliliters of 0.2 molar sodium chloride. I'm going to go ahead and calculate how many moles that is. So 50.0, unless they want us to assume, no, it can't be. Okay, 50 milliliters. So I'm going to convert that to liters, so that's 0.0500 liters times a concentration of 0.2 molar is 0.0100 moles of sodium chloride. That looks like an L, it should be a C. And now it just looks like a backwards D. Oh well. We've got 0.1 molar silver nitrate also at the same temperature. So 100 grams of 0.1 molar, they must have meant 100 milliliters again, so that's 0.100. Wait, how many decimals do I have? Oh, 4. 0.1000 times, it's 0.100 molar, so, oh, interesting. No limiting reactant here, we have exact amounts. So both of these are at 24.1 degrees Celsius initially. And their temperature goes to 25.2 degrees Celsius. Looks like I haven't used much green, so lost my train of thought again. Oh, right, I wanted to write the balanced equation, so we've got sodium chloride plus silver nitrate forms sodium nitrate plus silver chloride, and of course the silver chloride is going to precipitate out as a solid. All of these will be aqueous. Okay, let's see what we can do. So temperature went up to there, and they gave us the specific heat of the solution was 4.2. See, solution was it 4.20? Yeah, 4.20 joules per gram. I don't think we've used Kelvin in a while, so joules per gram Kelvin. Okay, then, okay, that seems to be it. I don't know why, but I felt like this would involve more steps. Anyway, calculate the Q for the solution. Which has to be a result of the energy change due to this reaction. Let's see, that's going to be mass of the solution. Ah, that is it. That is it. Okay, so when they said 50 grams and 100 grams, they really did mean for you to treat it as two solutions with a density of 1 gram per milliliter. So they're treating the densities of the two solutions mixed as being equal to the density of water. Okay, now I'm clear on that. I wish they could have cleared it up more. They could have added a line saying assume the densities of the solutions are equal to 1 gram per milliliter. Okay, but now I get what they're hinting at. So what's the mass of the whole solution? Well, we mixed 50 grams with 100 grams, so there should be 150 total grams of solution. In fact, it was 50.0 plus 100.0, so it's 150.0 total grams. Specific heat is 4.20. And the temperature change is 25.2 minus 24.1 is 1.1 Celsius degrees. I don't know why I bothered writing that, especially since I haven't been in the habit of doing that for this whole video. Let's see. And yeah, that's all they wanted. 150.0 times 4.20 times 1.1. Oh, wait, I should have done that in steps. 150 times 4.20 is 630, and then times 1.1 is 693, which I have to round to 690 because 4, 3, 2 sig figs, so yeah, 690 joules. Or, more properly, 6.90 times 10 to the 2 joules. Or 0.69 kilojoules might be even better. 0.69 kilojoules. Okay, and bonus question from me is calculate the molar heat of reaction. calculate delta H reaction. So it should be the kilojoules per 1 mole of NaCl, or per 1 mole of silver nitrate, or per 1 mole of sodium nitrate, or per 1 mole of AgCl. Balancing coefficients are all 1s for this reaction. Okay, since I've got equal moles of both, then it's 0.01 moles of sodium chloride, 0.01 moles of silver nitrate, 0.01 moles of sodium nitrate made, and 0.01 moles of silver chloride precipitated. So no matter how you slice it or dice it, it's 0.01 moles. 0.69 kilojoules divided by 0.01 moles gives us 69 kilojoules. Delta H reaction is 69 kilojoules per mole. Or just 69 kilojoules if you prefer. Or wait a minute, sign conventions. I almost forgot. So the solution warmed up, which means that the atoms overall lost energy. This should be negative 69 kilojoules per mole. And that should be negative 0.69. No, this shouldn't be negative because this is Q solution. If it was Q atoms, then that would have been negative 0.69. Okay, so I need a negative there, don't need it here. Okay, we're good to go. But yeah, so this all demonstrates how you can use calorimetry as a technique to determine heats of reaction. If you wanted to find the heat of reaction of something and it's not listed in your data table, but you have a nice lab and you have all the fancy equipment, you can determine whatever information you don't have just by setting up a calorimetry experiment, assuming of course that your substances can actually be dissolved. If you're working with insoluble substances, then you might need something else. Let's see, do we want to do 27? The addition of 3.15 grams of barium hydroxide octahydrate to a solution of 1.52 grams of ammonium thiocyanide in 100 grams of water in a calorimeter caused the temperature to fall by 3.1 degrees Celsius. Should say Celsius degrees, but I digress. Assuming the specific heat of the solution and products is 4.20, calculate the approximate amount of heat absorbed by the reaction, which can be represented by the following equation. So pretty much the same as what we did before. The bonus question that I added to number 26, basically. Calculate delta H reaction. We've already seen that. So let me see what else I have for you. What else do I have set up here? Okay, I think it's time to talk about how we can do a constant volume process. So what you see here in front of you is the apparatus for what's called a bomb calorimeter. A bomb calorimeter. And the reason it's called a bomb calorimeter, apparently, based on what I looked up, is that it's usually used for calculating heats of combustion, and the combustion that happens inside of a bomb calorimeter is kind of like a tiny explosion, so it's kind of like a bomb. So yeah, that's why it's called a bomb calorimeter, apparently. But yeah, the setup, you can see it in front of you. They've got some electrodes connected to it. Those will create a spark that will start the reaction and get it going. They've got basically this water bath surrounding that silver cup that you can see right there in the middle of the figure, in the middle of side B of the figure, I should say. And that cup, that silver cup thing, that's what's called the bomb. It's kind of like an airtight, sealed container that doesn't allow for any sort of volume change while the reaction happens, but it still allows heat from the reaction to leak out into the water surrounding it. And based on the temperature change of the water, and also along with knowledge of the heat capacity of this silver cup thing, as it's called, a bomb, you can determine the heat of reaction under constant volume conditions. So this is how you would go about calculating QV. Okay, so let's see a problem involving a bomb calorimeter. You probably won't have to do this in class, even if you are a college student. You definitely won't have to do it in high school. Unless, actually, do they do it in IB chemistry? I'm not sure. But I definitely know they don't do it in AP chemistry. And AP chemistry is said to be tougher than IB chemistry, so based off of that, I would assume you don't need to do it in IB chem, but we're doing an example anyway, so either way, you have no reason to fear. So let's see, what do we have for bomb calorimeter problems? Okay, here's something. So, wait, this doesn't look right. Is that the right one? Yeah, okay. So number 30, it says when 1 gram of fructose, a sugar commonly found in fruits, is burned in oxygen in a bomb calorimeter, the temperature of the calorimeter increases by 1.58 degrees Celsius. If the heat capacity of the calorimeter and its contents is 9.90 kilojoules per Celsius degree, what is Q for this combustion? Okay, simple enough. What about 31? When a 0.740 gram sample of trinitrotoluene, or TNT, is burned in a bomb calorimeter, the temperature increases by that much. The heat capacity of the calorimeter is 534 joules per Celsius degree, and it contains 675 milliliters of water. How much heat was produced by the combustion of the TNT sample? Okay, I see. So 30 and 31, there's a slight difference between them, but they're both actually pretty easy if you know what you're doing. What about 32? Oh, I remember. Okay, 32, so it'll require some dimensional analysis and stuff, but it's nothing too different. Okay, let's do 30 and 31. So 30 says if the heat capacity of the calorimeter and its contents is 9.90 kilojoules, what is Q for this combustion? Simple enough. Q equals mc delta T. Or, whoops, lowercase c. Q equals m little c delta T, or big C times delta T. In this case, they gave us big C not just for the calorimeter itself, but also the water inside. So the water and the cup, the bomb. So they've got, let's see, 1.58 degrees Celsius is the temperature change, and the heat capacity of the calorimeter and all of its contents, 9.90 kilojoules per Celsius. So all you have to do is say Q equals 9.90, and that's in kilojoules per Celsius. I'll keep it in kilojoules. and multiply it by a temperature change of 1.58 Celsius degrees. I think I missed that the first time I read it. They made a mistake there too. Of course, they're mistaken everywhere here. So what is Q for the combustion? I don't see why it even matters that it's 1 gram. I think they should have asked for the heat of combustion instead, which we can do. But 9.90 times 1.58 is going to round to 15.6 kilojoules of heat. So that was heat released by the fructose. So Q of the calorimeter was 15.6, which means Q of the fructose, I'll just abbreviate it FRUC, would have been negative 15.6 kilojoules. And although they didn't ask this, I'm going to ask it as a bonus question. What is the heat of combustion of fructose? Is it really C6H12O6? Because that's glucose. Oh, great. They even got... Oh, hold on. I didn't even switch screens for you guys, did I? Well, it was a simple process. As long as you were listening, you probably saw what I was doing anyway, in your minds. Anyway, fructose is not C6H12O6. That's glucose. Hold on, let me Google the formula for fructose. Let's Google it. And while I'm at it, I might as well just get the molar mass from Google. Okay. Oh, no, it is. It is C6H12O6. Okay, then it probably has a different structure. So the way that the carbons, hydrogens, and oxygens are connected is different. Okay, fine by me. Now I know. Fructose and glucose have the same molecular formula. Those are what we call isomers. We'll learn about isomers in the last chapter, actually, unless I decide to cover it earlier, which is the organic chemistry chapter. Okay, so it's about 180.16 grams for the molar mass of fructose. 180.16 grams per mole. So if I've got 1 gram of the stuff, then 1.0 grams divided by 180.16 is 0.0056 moles. We've got 0.0056 moles of fructose and 15.6 kilojoules released by less than 1/100th of a mole. Let's see, if I do negative 15.6 divided by 0.0056, then I get roughly negative 2,800. Delta H combustion is equal to roughly negative 2,800 kilojoules per mole of fructose, or, if you like, negative 2.8 megajoules per mole. We don't get to use the mega prefix very often in chemistry. So there it is. Okay. Let's see. So after that, we've got 31. So 31 in terms of the calorimetry part shouldn't be too hard. We've got 0.74 grams of TNT burned in a bomb calorimeter. The temperature increases from 23.4 to 26.9. So that's a temperature change of 3.5. The heat capacity of the calorimeter is 534 joules per Celsius, and it contains 675 milliliters of water. How much heat was produced by the combustion of the TNT sample? Okay, so for this one, we need to get the total heat capacity first. So let's see. We already have the heat capacity of the calorimeter part, but not the water part. So C total for the whole apparatus should be C of the calorimeter plus C of the water, if I'm understanding this correctly. And let's see, that's going to be 534 joules per Celsius for the calorimeter, plus for the water, they said it was 675 milliliters of water. We're going to assume that the density of water is 1 gram per milliliter, so that's 675 grams times the specific heat capacity of water is 4.184. And let's see, that'll be 534, or wait, no, let's do 675 times 4.184 first, and rounding that to 3 sig figs would be 2820. So 534 plus 2820, that's with 3 sig figs. So if I were to write it in scientific notation, it would be 0.534 times 10 to the 3 plus 2.82 times 10 to the 3. So we've got 3 decimals, 2 decimals. After adding, we should round to 2 decimals. So 2820 plus 534, that would be 3.354 times 10 to the 3. Rounding to 2 decimals, 3.35 times 10 to the 3. And let me see, so I guess I'll write it as 3350, and that was in joules per Celsius or joules per Kelvin. Okay, and now that we have that, we can take the temperature change, which was 3.5. Delta T was an increase of 3.5 Celsius degrees, and multiply and get, wait, is that right? Did I get my units mixed up? No, it is in joules. Okay. Multiply that by 3.5, so C, big C times delta T, 3.5 times 3350 is a big number, which would round to 12,000 joules or 12 kilojoules. So Q equals C total times delta T equals approximately 12 kilojoules. Okay, there we go. And yeah, that's bomb calorimetry for you. Okay, so now I guess all we have left is a bit of cleanup, connecting these topics to previous topics we've covered, and also a little bit of a bonus section on nutritional calories. So let's go ahead and take a look at, first, let's take a look at some stoichiometry problems involving heat. let me see, were these the ones? No, these are all for exactly 1 mole of substance, which is basically the heat of formation. Okay, so those were useless problems. I don't know why I listed them. Was it this set? Probably. If it's not this set, then I'll have to grab some from my other book. Okay, no, this one looks right. So 45 says, how much heat is produced by burning 4 moles of acetylene under standard state conditions? So acetylene is C2H2, if I remember correctly. No, wait, let me think here. Acetylene, is it C2H2 or C2H4? No, C2H4 is called ethylene. Yeah, acetylene I'm pretty sure is C2H2. Of course, if I'm wrong, I'll correct myself in a pinned comment like I always do. Okay, acetylene C2H2. So, if we burn 4 moles of acetylene, how much heat is produced? That's the question. So for this kind of problem, you are going to need to use, data tables to determine the heat of reaction. But yeah, so we've got ourselves a simple stoichiometry problem there. If we've got 4 moles of acetylene, 4 moles of C2H2, and I'm assuming it's going to be in the form of a gas, then how much heat is produced? So first we need to calculate the heat of combustion of acetylene, or just the heat of reaction for the combustion of acetylene. So let's write that reaction, C2H2. Oh, wait a minute. Okay, I suppose the water that will form will be a vapor. Okay, C2H2 gas plus oxygen gas yields carbon dioxide gas plus water vapor. Let's balance it. So if I put a 2 here and a 1 here, that will give me an odd total oxygen, so I need a 2 here and a 4 here and a 2 here. And then that's 8 plus 2 is 10 oxygen, so I'd need a 5 there. Okay. And let's go ahead and look up the heat of formation of C2H2. Carbon should be up there in the first few. Carbon, carbon, carbon. Okay, C2H2, where are you? There you are, 227.4 kilojoules per mole. 227.4, positive 227.4 kilojoules per mole. Okay, oxygen, of course, we know is 0, and then for water and CO2, where's CO2? Well, I can just look them up from that previous page where I had them. That would probably be quicker. So, let me switch back to there. And let me dig up that earlier problem where we actually did use the... Was it here? No. 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 Was it this one? Yes. Okay, so water, negative 241.82. I'll just copy that down. And carbon dioxide was negative 393.51. And this is how sloppy my handwriting gets when I try to write on my lap. Oh well. Kilojoules per mole. Kilojoules per mole. Probably don't need to write that every single time, but, you know, habits. And of course, oxygen is 0 because it's a pure element, and it's in its naturally occurring form. Let's see here. So yeah, just calculate delta H reaction. And that's going to be negative 393.51 times 4 plus negative 241.82 times 2. That should still give me 2 decimal places. Minus 2 times 227.4. And that should round to 1 decimal place, so that's negative 2512.5 kilojoules for this reaction, kilojoules per mole. That's an exothermic process. Most, if not all, combustion reactions are exothermic processes. So, yeah. If I have 4 moles of C2H2, then what I can say is for every 4 moles of C2H2, well, for every 2 moles of C2H2, we've got 2,512.5 kilojoules of heat produced. Okay, that wasn't too bad. So divide by 2, multiply by 2512.5. 4.00 times 2512.5 over 2. So I guess I'll just fix that and make it a 2. If I round to 3 sig figs, that would be 5,030 kilojoules, or 5.03 times 10 to the 3 kilojoules, or 5.03 megajoules. Megajoules. A megajoule is 1,000,000 joules. A kilojoule is 1,000 joules. So when you've got 1,000 kilojoules, 1,000,000 joules, 1,000,000 is 1,000,000. That's not very apparent. We don't really think about that very often, how 1,000,000 is 1,000,000, or maybe that's just me. Okay, so 5.03 megajoules. And, of course, let me see, what was the question? The question was how much heat is produced by burning 4 moles of acetylene under standard state conditions. So you might be wondering why I didn't keep the negative sign here. This is super important. So their question was how much heat is produced. So they're already assuming that it's released. So if I gave a negative answer here, then basically I would be telling them that negative 5.03 megajoules is produced, and to say that a negative amount is produced would mean that it's absorbed, which doesn't make sense. So whenever you see the words how much in these problems, always go for the absolute value. Always go for the absolute value. Do not include negatives. If it was asking for the heat of reaction, that could be positive or negative. If they're asking how much heat, then they just want the amount, they don't want the sign. You might see that on multiple choice exams. You might see the negative choice listed as an answer choice, and a lot of people fall for it. You're not going to be one of those people. Or maybe I should say more broadly, you guys are not going to be among those people. It's not like I'm talking to one person here. But yeah, let's take a look at another one. So 46, how much heat is produced by combustion of 125 grams of methanol under standard state conditions? So that one adds an extra step, which is you have to convert from grams to moles, but we also have to calculate the heat of reaction. So yeah, I'm thinking of doing 46. What does 47 say? How many moles of isooctane must be burned to produce 100 kilojoules of heat under standard state conditions? I'm not quite sure off the top of my head what isooctane is, so I'll skip that. What mass of carbon monoxide must be burned to produce 175 kilojoules of heat under standard state conditions? Okay, maybe do that one. And 49. When 2.5 grams of methane burns in oxygen, 125 kilojoules of heat is produced. What is the enthalpy of combustion per mole of methane under these conditions? We already did heat of combustion before, so we'll skip 49, but let's take a look at 46 and 48. So 46, how much heat is produced from combustion of 125 grams of methanol? Methanol is CH3OH. CH3OH. And if you're wondering why it's not written as CH4O, why the H3 and the H over there are not combined, well, it's because of the structure. I think I showed that before in a previous video at some point, maybe for acetic acid. But yeah, for a lot of organic compounds, their names or their formulas are written in a way that makes it easy to figure out their structure. CH3OH looks like this. So that's your CH3 part of it, and then it's connected to an OH, like that. We'll figure out how to draw Lewis structures for small molecules in a couple chapters, but for bigger molecules, for organic molecules, again, that'll have to wait until the final chapter, unless I decide to reorder the last few chapters for whatever reason. I probably won't, but you know, you can hope. Anyway, CH3OH combusts with oxygen, giving us carbon dioxide and water. I'll assume again that the water is released as a vapor. And methanol, I believe, will be in liquid form, but we'll have to see what's in our data table. So let me actually go to that. So our data table says, where's methanol? CH3OH, yeah, there it is in liquid form. Wait, oh, I have it. Wait, did I misread? Oh, we've got it both as a liquid and a gas. Okay. Let's do it in the liquid form. So negative 239.2. Negative 239.2. Kilojoules per mole. Copying that down. And okay, off we go. So 125 grams of methanol. How much heat is produced by that? First we need to calculate delta H reaction. So I already know carbon dioxide and water vapor from up here, but I need to balance this equation. So let's see. I have an odd number of oxygen here, so this time 1 and... Okay, so that's not going to work. So I will need to double this because 4 hydrogens, I'd have Yeah, that would make it even. Okay, so I have to double this, which means 2 carbons there, and 2 times 4 hydrogens, that would be 8, so I need 4 there. And 4 plus 4, that's 8 oxygens. We've got 2 oxygens already in the methanol, so we only need 6 more, so this should be times 3. Though I guess we could ignore balancing the oxygen now that I think about it. Yeah, because it has no influence on the delta H. Well, I don't know. Probably better to stay on the safe side and just balance it anyway. It's not like it takes that much work. Okay, so for carbon dioxide, we've got 2 times negative 393.51. Plus for water, we've got 4 times negative 241.82. And then subtract from that negative 239.2. And that's negative 1515.1. And it's already in 1 decimal place, so we're good to go. Delta H for this reaction is negative 1515.1 kilojoules per mole. So then we can calculate. If we've got 125 grams of methanol, then I can say 125 grams times, let's see, what's the molar mass of methanol? So we've got carbon 12.011 plus oxygen is 15.999 plus 4 hydrogens, 4 times 1.008 is 32.042. 32.042 grams for every 1 mole of methanol. Okay, so that's grams of methanol to moles of methanol. And then from moles of methanol, we need to get to kilojoules of heat. So for every, according to the balanced equation, 2 moles of methanol produces 1515.1 kilojoules of heat. And the rest is just plugging into your calculator. I don't think you need me to do that anymore. Then again, I've been doing it for this whole entire video, so why not? 1515.1 over, well, hold on, 125 over 32.042 rounds to 3.90. 3.90 over 2 is 1.95, and then times 1515.1 rounding to 3 sig figs is 2950. 2950 kilojoules, or 2.95 megajoules, so that I clearly show that it's 3 sig figs and not 4. Alright, so that takes care of that one. What was the other one I wanted to look at here? Was it 48? What mass of carbon monoxide must be burned to produce 175 kilojoules of heat under standard state conditions? Okay, what mass of carbon monoxide? So so basically the reverse of the previous problem. So we've got 175 kilojoules of heat. So we've got 175 kilojoules of heat already. And we need to figure out how many grams of carbon monoxide that's going to take. Okay, so combustion of carbon monoxide. Well, if you burn carbon monoxide, you're just reacting it with oxygen, so CO plus O2 gives you CO2. And that's it. So, balancing, I would just need a 2 here and a 2 here. 2 carbons, 2 carbons, 2 plus 2 is 4 oxygens, and 2 times 2 is 4 oxygens. Okay. If you're not that quick with your balancing, well, you don't need to be as quick as I am, but being able to balance shorter equations like this quickly is a skill worth working at. So anyway, carbon monoxide I need to look up. So let's take a look at our data tables. Carbon monoxide. Carbon monoxide, where are you? And carbon monoxide should be in the form of a gas. It's not there. It can't not be there. Maybe I'm just missing it. Oh, maybe it's up here. Okay, there it is. It's on a different page. Carbon monoxide as a gas is negative 110.52. Negative 110.52. I'll have to write it above because I planned this poorly. And then oxygen is nothing, and then carbon dioxide was negative 393 was it 51? Yeah. I've seen it so many times I'm starting to memorize it. Okay, copied all that down. Let's switch back to our camera. Okay. And I'll get the molar mass of carbon monoxide later. So first I want delta H reaction. So that's going to be 2 times negative 393.51 minus 2 times negative 110.52. Should have 2 decimal places, so negative 565.98. Delta H reaction is negative 565.98 kilojoules per run of the reaction. Per mole of reaction, not per mole of any individual substance, unless it happens to have a balancing coefficient of 1. I know you've probably gotten that by this point, but you never know. Somebody might have skipped most of the video and just jumped straight to the end. Of course, I don't have to cater to those people, but I'll try to be helpful when I can. Where was I? Okay, so now I can... Oh, let's get the molar mass of carbon monoxide. So 12.011 plus 15.999, 28.010. So that's the molar mass of carbon monoxide is 28.010 grams per mole. Okay, so 175 kilojoules of heat is released. So we've got for every 565.98 kilojoules of heat released, 2 moles of carbon monoxide have reacted. And then for every 1 mole of carbon monoxide, that's 28.010 grams that have reacted. So the total reacted grams are 175 times 2 is 350 divided by 565.98. Rounding to 3 sig figs is 0.618. times 28.010 over 1, which doesn't change anything, so 17.3 if I round to 3 sig figs. 17.3 grams of carbon monoxide. All right. Was there anything else I wanted to do from that page? No, I think not. Let's take a look at a problem involving limiting reactants. We better not forget these skills. So, number 50 says how much heat is produced when 100 milliliters of 0.25 molar hydrochloric acid with a density of 1 gram per milliliter and 200 milliliters of 0.15 molar sodium hydroxide, same density, are mixed. Ooh, okay, so this was what I was hoping for earlier when we had, what was it, sodium chloride and silver nitrate. This is what I was hoping for, something with a limiting reactant. So hopefully this doesn't turn out to be the same as that problem. I'm pretty sure I read it beforehand and made sure that that wouldn't happen. Yeah, it won't happen. Okay, so, and look at that. They gave us the delta H reaction, so we don't have to calculate it from the data tables. How nice of them. Would have been great if they did that for the last couple problems. HCl plus NaOH gives us that stuff, negative 58 kilojoules. If both solutions are at the same temperature and the heat capacity of the products is 4.19, they should have said specific heat capacity is 4.19 joules per gram Celsius. How much will the temperature increase? Okay, let me go ahead and switch to my camera, and let's see. So they gave us the delta H is negative 58. They gave us the balanced equation. Everything is 1 to 1 to 1 to 1. So we've got 100 milliliters of 0.25 molar HCl. 100 milliliters is a tenth of a liter, and liters times molarity gives you moles. So 0.100 liters times, what was it, 0.250, that will give us 0.0250 moles of HCl. And then we've got 200 milliliters, so that's 0.200 liters times 0.150 moles for every 1 liter, so 0.2 times 0.15 would be 0.0300 moles of NaOH. Oh, I guess the negative 58 kilojoules, the delta H that was given, can be called the heat of neutralization, since the reaction is an acid-base neutralization. But anyway, so that was negative 58 kilojoules per mole. And yeah, I should also say that the total mass would be, let's see, 100 milliliters plus 200 milliliters, both at a density of 1 gram per milliliter, so that's 300 grams is the total mass, the mass of the whole mixture. So let's see. Limiting reactant here is the HCl. For every 1 mole of HCl, you can react with 1 mole of NaOH. Since you've got less HCl than NaOH, the HCl runs out first, and you'll have 0.0050 moles of leftover sodium hydroxide. Okay. So we're going to base our calculations on the HCl. and say that Q is going to be equal to, well, maybe I should write it like this. So 0.0250 moles of HCl. For every, according to the balanced chemical equation, it was 1 mole of HCl after balancing. Gives us 58 kilojoules of heat. So 0.0250 times 58 gives us 1.45, which I would have to round to 1.5 kilojoules to get 2 sig figs. Okay, so there's 1.5 kilojoules of heat released, and then how much does it warm up then? So that's going to be Q for the solution. So 1.5 kilojoules of heat is released by the reaction, gets absorbed by the solution, which just so happens to also involve the same atoms that just reacted. So they get warmed up too. Let's see, 1.5 kilojoules, I should convert that to joules. So Q solution is 1.5 times 10 to the 3 if converted to joules, which equals the total mass of solution, 300 grams. Or was it 300.0? No, it's 300. So 300 grams times the specific heat was 4.19. Yeah, 4.19. And they wanted the temperature change. Okay, yeah. So delta T is what we're solving for. Easily done. 1.5 times 10 to the 3 divided by 300 is 5.0, and then 5.0 divided by 4.19 is 1.2. Delta T is equal to 1.2. Let's call it kelvins this time. Kelvins, Celsius degrees, same thing. All right. So there was an example with a limiting reactant. I feel like I'm forgetting. Oh, I'm going to need to talk about molar heat capacity. Well, molar heat capacity will probably become more relevant in a later chapter, so I'll have a chance to talk about it then. No harm in talking about it now. So, we didn't see it in these problems, we didn't see it in this chapter, but later on we're going to see something called molar heat capacity, and basically it's the same as specific heat capacity, except it's per mole rather than per gram. So let's say we've got the specific heat capacity of water is 4.184 joules per gram Kelvin, or per gram Celsius. I'll go with Kelvin this time. So that's the specific heat of water, the C of H2O. But we can convert this to the molar specific heat of water, which is sometimes denoted by a subscript of little m, so C molar of H2O. What's that going to be? Well, all you have to do is basically convert the grams down here into moles. Depending on the substance, you should be able to calculate its molar mass. So for water, molar mass is approximately 18.02, give or take. So if I've got 4.184 joules per gram Kelvin, then I can do 4.184 joules over gram kelvins multiplied by every 1 mole of water is 18.02 grams approximately. So grams would cancel out, and I would have joules per mole Kelvin. So 4.184 times 18.02 is 75.40. 75.40, and that's joules per mole Kelvin. So sometimes you might be given the specific heat capacity as a molar heat capacity. And if it's given as a molar heat capacity, pretty much the same thing, except instead of Q equals mc delta T, what you would need to do, since you're not working with units of grams anymore, you can't use mass, you would use moles. Q equals N C molar delta T. So number of moles times molar heat capacity, or number of grams times regular specific heat capacity. This we will deal with in a later chapter. We'll end up having to use it occasionally, but no harm in introducing it early on, just in case your teacher happens to be obsessed with molar heat capacities or whatever. But I saw no sign of it in any of the textbooks that I have. Maybe I didn't read carefully enough, but I know it shows up later on, so there's that. Last but not least, and this is kind of just, what would I call it? FYI content. Probably not going to be the most important thing you need to know. Well, actually, I think they recently added it to the AP Chemistry curriculum. Just a little bit of questioning about nutritional calories. Anyway, let's take a look at a couple problems involving nutritional calories, and then we'll finally call it a conclusion to the video. I would say call it a night, but you might not be watching it at nighttime. I'm recording it at nighttime, but that's for me to know. 34 says a teaspoon of the carbohydrate sucrose, which is common sugar, contains 16 calories with a capital C, or 16 kilocalories, kcals. What is the mass of 1 teaspoon of sucrose if the average number of calories for carbohydrates is 4.1 calories per gram? So that one should be really easy to do. It's just a dimensional analysis problem. So we've got, let's see, what is the mass of 1 teaspoon if, okay, so 1 teaspoon has 16 calories. We've got 16 calories, or kcals, 16 nutritional calories in a teaspoon, and they say it's 4.1 nutritional calories per gram, so 4.1 kcals in every 1 gram. 16 divided by 4.1 is 3.9. 3.9 grams of sucrose fit in a teaspoon, give or take. There, that wasn't so bad. Let's do another one. 35. What's the maximum mass of carbohydrate in a 6-ounce serving of diet soda that contains less than 1 calorie per can if the average number of calories for carbohydrates is 4.1 calories per gram? Yeah, I don't know the conversion factor between ounces and grams, and I'm feeling too lazy to look it up, so we'll skip 35. 36. A pint of premium ice cream can contain 1,100 calories. What mass of fat in grams and pounds must be produced in the body to store an extra 1.1 times 10 to the 3 calories, or the 1,100 calories mentioned before, if the average number of calories for fat is 9.1 calories per gram? Okay, so 36 is basically the same as 34. 1,100 nutritional calories divided by 9.1 calories for every 1 gram, and that should do it. I think we can skip that one. Serving of breakfast cereal, 3 grams of protein, 18 grams of carbs, and 6 grams of fat. What's the calorie content of a serving? If it's 9.1 calories per gram for fat and 4.1 calories per gram for both protein and carbs. Okay, that one should be easy enough to do. Let's go ahead and do it. Note that this is not me encouraging you to become rabid calorie counters. I don't think calorie counting really works. I think if people are dieting correctly, they shouldn't need to count calories, but what do I know? Let's see. Where was it? Number 37. So it was 3 grams of protein. And 18 grams of carbs. And 6 grams of fat. And of course, we would have, let's see, so protein and carbs are approximately the same, 4.1 nutritional calories per gram. So that's for both of these. And then for fat, it's 9.1 nutritional calories per gram, also known as kilocalories. I know I've said that plenty of times, but the more I say it, the more it'll stick. So let's see, 3 grams times 4.1 calories per gram and 18 grams times 4.1 calories per gram. So 21 times 4.1 is 86.1. Wait a minute. Those aren't measured, are they? Okay, I'm going to treat the 3 and the 18 like exact numbers, and the 6. Although there shouldn't be a way to exactly measure the grams, but it just feels like the way this problem is written, they intended for it to be exact, but maybe my judgment is off. So 86.1 calories from these guys, and then 6 times 9.1 gives me 54.6, and if I add those, then that's a total of 140.7 nutritional calories. 140.7 nutritional calories, or 140.7 kcals. Wouldn't it be great to run on a treadmill or exercise bike just until it showed that you burned 1 nutritional calorie, and then get off of it and prank a friend by telling them that you burned 1,000 calories? Probably wouldn't be that funny, but you can try it. Tell me the results. It'll be a psychological experiment. So that was 37. 38. Which is the least expensive source of energy in kilojoules per dollar? Ooh. A box of breakfast cereal that weighs 32 ounces and costs $4.23. Or a liter of isooctane with a density of 0.6919 grams per milliliter that costs 45 cents. Compare the nutritional value of the cereal with the heat produced by combustion of the isooctane under standard conditions. A 1 ounce serving of the cereal provides 130 calories. Okay, well, again, like I mentioned before, I don't know what isooctane is, and I'm too lazy to look it up, but at least to calculate the kilojoules per dollar for the cereal, at least we can do that part. And if you want to look up isooctane and do the rest of this problem yourself, you're more than welcome to do that. I'm not going to go out of my way and bend over backwards for some FYI problems. these are probably not going to show up on most people's exams, and if they do show up, it'll probably be like one multiple choice question worth a point. So it was 32 ounces, 423, 32 ounces, and $4.23. And they said a 1 ounce serving of the cereal is 130 calories. 1 ounce equals 130 calories. Okay, so we've got everything we need for the cereal at least. So we've got 32 ounces for every 1 ounce. We've got 130 kcals, which is 130 times 10. Well, I'll just say kilocalories for now. And then we want it in kilojoules, right? They wanted it in kilojoules per dollar. So to convert from kilocalories to kilojoules is the same way you convert from calories to joules. 1 calorie is 4.184 joules, so 1 kilocalorie is 4.184 kilojoules. Okay, and they just wanted it in kilojoules, right? Yeah, kilojoules per dollar. So we can calculate the total kilojoules now. So 32 times 130 times, well, let me multiply those first. So that's 4160, which I'd round to 4200, times 4.184, which is an exact conversion, but that's 18,000. That's going to be 18,000 kilojoules. Divide by 423, so 18,000 divided by 423 gives us about 4,200, or no, 4,300 rather, since the 5 rounds it up. 4,300 kilojoules per dollar. 4,300 kilojoules of energy per dollar spent. Must be some really high-powered cereal. Either that or I don't have a really good common sense grasp of what 4,300 kilojoules even is. Okay, I think with that we can wrap things up. Let me check my notes. Did I forget to mention anything? Oh, there is one last thing to mention. Okay, glad I checked my notes. So, there is one last little thing I forgot to mention. It's probably not going to be the most consequential thing for a chemistry student, but there's this notion of state functions. I should have mentioned this way back in the beginning when we were talking about internal energy and stuff. State functions. State functions. So what on earth is a state function? Basically, it's anything that's a function of your current state, or anything that is a function of the change between your next state and your previous state. And what that means in simpler terms is anything that just depends on the current state of an object, or in our case, a substance usually. So the internal energy is a state function, and enthalpy is a state function. internal energy and enthalpy are state functions, which is to say that their value doesn't depend on how you achieve the change, it just depends on what the change is. So basically, think of position. Think of position. Let's say you're trying to cross a road. So let's say this is a road and here's a person trying to cross it from point A. They want to get from point A to point B. So they can go all sorts of different ways from point A to point B. They can go this way and then cross the road like that. Or if the road happens to be clear, they could just go straight like this way. They could take this weird curvy path. They could go this way and then cross, and then this way and then cross back and do something weird and wild and then eventually get to point B. But no matter which path you take, at the end of the day, the change in your position is the same. Your position has changed by this much in this direction. For those of you who know your physics, that's what we call displacement. So you got to point B regardless of the path you took. Now, depending on the path you took, you might have spent more energy. If you took that last path I drew, then you probably walked a greater total distance to get to the same place. So we would say distance, and the energy you spent getting from A to B is not a state function. It does depend on how you chose to get there. How you chose to get there. This is what happens when I talk too fast. Enthalpy and internal energy are state functions. They do not depend on how you get from one state to another. They only depend on the difference between the initial state and the final state. This is especially easy to demonstrate for enthalpy, because remember what we did earlier with Hess's law. Let me see if I can dig up the sheet where we did that. So something like this. When we did this over here and we combined these three equations and added them to get the delta H overall for this green equation, we could have also calculated the delta H for this green equation using the normal method with heats of formation and data tables, and assuming that we were careful with our sig figs and neglecting some rounding errors, we would have probably gotten approximately the same answer. We probably would have gotten the same delta H regardless of the path taken. If there is a difference, it'll just be a slight difference because of a difference in rounding and numbers of sig figs and all that good stuff. But yeah, it shouldn't matter how you go about calculating it, which is why Hess's law works. If you don't know the heats of formation, this other route should still give you the same delta H value. And in fact, you can, if you have the equipment and you have access to a lab, you can do this process in two different ways and actually calculate the heat and prove to yourself in the physical real world that you do indeed get the same delta H, whether you do this all in one step or whether you do it in 3 steps. As outlined here, the total energy cost is the same. So that's delta H, it's a state function. Delta E, I guess you could say, here's a very, very crude example. Let's say you wanted to get a delta E of 1,000 joules. Well, you could either have your system absorb 1,000 joules of heat, that's one way to do it, or you could do 1,000 joules of work on your system, or you could do 500 each, or you could do 200 of one and 800 of the other. There are many different ways to achieve the same amount of internal energy change. So that's state functions. It's just something that you're going to want to conceptually understand. it's not really something that most chemistry instructors will hound you for not knowing. You can probably get away with not knowing anything about what a state function is until you get to your physical chemistry class in college. You probably won't be going there unless you're actually doing chemistry in college, but if that's you, then you definitely can't get away with not understanding this, but you'll have to take physics beforehand, so you'll probably get familiar with other state functions like potential energy and whatnot. Anyway, now I'm rambling too much. This video has gone on for long enough. I hope you all benefited from this video and from all the other videos, and yeah, I'm gonna try and find the time to put out more of these videos, but it is September. Everybody's back to school. I might be too busy to put out these videos as quickly as I was doing before. Not that I was putting them out that quickly, but I'll try to go for, I don't know, one video every week or every other week. I'll see what I can do. But the topic for next time is going to be the electronic structure of atoms. So we're going to talk about waves and photons and all that good stuff, and then we're going to transition into talking about orbitals and the quantum mechanical model of the atom. So that's what you can look forward to next time. This has been Al the Tutor, reminding you that ignorance is not bliss. Take care, and I'll see you in the next video.